Good afternoon, everyone. My name is Samuel, and allow me to say on behalf of my fellow organizers, Yang, Arsha, Antoine, Ernesto, Ivan, Rahul, Bernard, and Andrew, it is a great pleasure to welcome you to the end of End-to-End, a video understanding pentathlon. We have a glorious array of exciting talks ahead, covering a range of video-related topics and presentations describing some of the creative ways that the top-ranked participants used in the entries for the challenge. Let's start with the big picture motivation. Our goal is to develop systems that can achieve higher level comprehension of videos. That means not just objects, but also complex actions, events, and long-lasting narratives. Computer vision has made truly tremendous progress at core tasks, with CNNs trained end-to-end for classification, detection, and segmentation. But extending these methods for higher level tasks is computationally very expensive. So one way forwards is to use frozen experts. These are representations that have been pre-trained on large-scale data sets. Caching features from these models enables us to focus on key questions for higher-level tasks whilst dramatically reducing compute. Questions like, how do we make the best use of temporal information? How do we exploit multiple modalities? And how do we achieve robustness across different domains? An additional benefit of reducing the computational barrier to entry is that it has the potential to allow broader participation outside of industry. This workshop has two simple objectives. First, to host a challenge, a video pentathlon that would support exploration of different ways of building video systems with pre-trained features. And second, to provide a forum for discussing ideas in video understanding. We have an exciting schedule ahead. We start off with an invited keynote from Chen Sun, then presentations from Shizhe, Linchao, and Jean-Baptiste, before a short coffee break. Then we shall have an invited keynote from Vondrick, before launching into the results of the challenge and presentations from the top-ranking teams. Then another coffee break to keep our globally distributed eyeballs pried open, before two more invited talks, our final short caffeine hit, and the last invited keynote from Anna Rohrbach. All this, in terms of schedule, can be found on the website. In terms of protocol, we will aim to have everyone except the speaker and any potential questioners microphones muted. Please add your questions to the chat. This is also streaming to YouTube, and we will do our best to monitor the questions there. We are recording this workshop to allow others to access it later. Please turn off your video if you don't wish to be recorded. If you want to ask a question, please note it will be streamed on YouTube, but we can remove it from the recording that will be released later if you contact us after the workshop. If there are any questions, please feel free to let us know. These are my wonderful fellow organizers. We will do our best to get to all of the questions, but please bear with us as we try to get to grips with this brave new world of Zoom workshopping. If we do not get to your question, please email us afterwards and we will forward the questions to the relevant speaker. Okay, well then next, it is my great pleasure to introduce Chen Sun, a staff research scientist from Google. Chen has worked on a bewildering collection of ideas from vision architectures, spatial localization, temporal localization, and an array of video transformer-based magic. It is a great pleasure to have his presentation at this workshop. With that, we shall begin. It's time to transition to our head of seamless screen sharing, Antoine, who will share Chen's presentation. Okay, over to you, Antoine. Okay, great. We have audio.
We all know that deep learning and big data have revolutionized computer vision in the past few years. And this is especially true when recognizing atomic visual concepts, such as locating small objects, or recognizing the semantic labels of individual objects, or actions performed by individual actors. The standard approach is the so-called end-to-end training, where we design neural network architectures that directly takes images or videos as inputs and design loss functions with corresponding tasks, such as classification, as shown here. Other tasks include localization or dense prediction. After the loss is computed, it is backpropagated to all the previous layers of the network. It turns out that end-to-end training benefit a lot from huge data. We did an empirical study in 2017 where the training data comes from 300 million noisily labeled images available on the internet. And here in this figure, I'm showing the number of examples in log scale on x-axis, the downstream object detection accuracy on y-axis. We can see that there is a log linear relationship between the two, with no saturation even at 300 million images. So for supervised deep learning, it seems that the more data, the merrier. It has also been recently shown that the big data sets, the big data sets are particularly powerful when the neural network have huge capacity, and that even unlabeled image data sets can lead to competitive performance using self-supervised learning objectives. Fortunately for us, they also show that these features are transferable to a wide range of downstream tasks, even for ImageNet, even using a linear classifier as a task decoder works pretty well. And due to the huge amount of resources required and hardware constraints for end-to-end training, and thanks to the promising results on transferring pre-trained visual features, a natural question to ask is that what high-level computer vision tasks can we accomplish by building on top of these powerful vision modules? As indicated by the title of this talk, we aim at developing algorithms to connect the dots of individual atomic visual concepts and provide a deeper and richer understanding of the visual world. One such example is human-object interaction, where the goal is to ground detected actions with interacting objects, such as plate for eating or the listener for listening. We can also treat many tasks, such as in vision and language learning, as an attempt to connect the dots, where one goal is to learn to discover the semantic correspondence between sentences and video clips. Finally, many events involve multi-agent interactions, such as sports games, self-driving cars, or even video games. We not only want to recognize and locate the individual agents, but also design tools to allow them to interact with each other. So all these three examples or three tasks I just mentioned require a structured representation of the visual world. Such representation has clear benefits, such as being interpretable, where one can design a graph structure and associate the nodes and also the edges to physical entities and their physical relations. And also compare with convolutional neural networks, a structured representation able to capture long-term relations, such as entities that are far away with each other, either spatially or temporally. And finally, it provides an abstract view of the visual world, and it enables us to naturally incorporate the pre-trained visual features or pre-trained visual detectors. In this talk, I will go over three examples which clearly benefit from the structured representation. And the first example is multimodal temporal representation learning. Our main motivation is that many people nowadays upload the so-called instruction videos to the internet, and they use cameras to capture what they are doing and pair with visual or very useful instructions or narrations that are closely related to visual content. And thanks to platforms such as YouTube or TikTok, the content is abundant and purely up to date. The question then becomes, how can we distill this useful information from these unlabeled videos? Let's first take a look at what we have from these videos. We have frames and audio signals that they are temporally aligned. We can also apply an off-the-shelf ASR algorithms to convert the audio to text information. We then want to establish the cross-modal dependencies between visual and language inputs. In this example, it will be between the middle video frame, the description moving around your pegboard. We are also interested in temporal dependencies on how human activities unfold over time, such as from the first video clip to the third video clip. So both the cross-modal and temporal dependencies are long-term dependencies, which can be established between nodes that are far away from each other in the sequence. And what would be the good tools to model such long-term dependencies? One option is to just use RNNs, recurrent neural networks. And given sequential observations X, it recurrently updates the hidden states based on the previous current observation and the previous hidden state. And we know that it is challenging, at least for vanilla recurrent neural networks, to model long sequences. And also it requires us to define an ordering, which does not exist in cross-model case. We can also use convolutions such as one-dimensional convolutions for time, which frees us from defining the order. However, the convolution operation has a fixed kernel size, convolutions such as one-dimensional. And in this case, the receptive field is only 3. More recently, the self-attention operation has been shown very powerful for natural language processing. It's trying to learn a linear combination of all the input values from a sequence based on some learned similarity metric. And we can imagine it as a fully connected graph with learned edge weights or edge attentions. And we can do message parsing among the different nodes in the graph. And this gives us unlimited receptive field. Also, it has been recently shown that the multi-headed self-attention is at least as expressive as the convolution operations. Okay, now that we have the self-attention operation to model the dependencies, what will be a proper training objective to learn the cross-modal and temporal dependencies? We seek inspiration from the natural language processing community on how they model these sequence dependencies. One simple yet powerful training objective, as popularized by the Bird paper in 2019, is to predict missing words that are randomly masked out in a text sequence. In this example, in order to predict the word cute, we humans need to look at the relevant words such as dog, likes, and play. So we can see that this training objective encourages the model to capture semantic dependencies. For videos, we hope to do something similar. Here, I'm showing 6 video clips in a movement video. They are ordered in time. We want to mask out one clip, for example, the third clip, and ask the model to predict what's the missing clips. And what's make this task challenging is that unlike predicting words, it's unclear how to define the loss function for video pixels. Our first option is to apply a perceptual loss, where one can apply their favorite generative models, such as VAE or a GAN, to directly predict the pixels. We can then compare the generative pixels with the ground truths, for example, by doing maximum likelihood training. However, although there are huge progress in deep generative neural networks, it has been shown that generating pixels is very challenging for the unconstrained videos that we are interested in here. Besides, for the purpose of learning cross-modal and temporal dependencies, chances are that we do not care about the subtle details, such as maybe the layout of the kitchen or the color of the person's shirt. All we care is the action here, which is eating chocolate. And these 3 clips, although their visual appearances are quite different, should be considered as equally good. This indicates that it's not only challenging, but also not necessary to reconstruct the subtle details. Instead, we design a loss function based on high-level semantics. What we do here is as follows. For each of the video clips, we apply pre-trained deep neural network to extract some visual features. We then use hierarchical k-means to group different video clips into clusters. And our hope is that semantically closed videos are grouped into the same clusters. We call this clustering step like the so-called tokenization. Here are some of the visualizations of the tokenization outputs. Each row corresponds to a video. On the left, I show the keyframe from the original videos. One is decorating a cake. and the other is bread and butter. And on the right are the visualizations after the tokenization step. For each frame, I show the image poses to the cluster centroids, so they could come from different videos in the training data set. We can see that the subtle details, such as maybe the color of the shirt or the outfits, are different. However, the high-level semantics, such as the K, the pegboard, and the action moving around, are preserved after this step. Here is the overview of our proposed framework. The inputs are tokenized video clips and the outputs of automatic speech recognition. They are temporally aligned. Some of the inputs are randomly masked out, and we pass the inputs to the bird or stack transformer layers. We name the framework as video bird due to the clear inspiration from the bird paper. And here is a more detailed view on the inputs and the target outputs of the video bird. Given input corpus, we can either keep the video intact and mask out some words, which is a way to force the model to learn object classifiers. Or we can mask out the video clips and ask the model to predict based on the language. And finally, for the videos without corresponding speech information, we can use video-only inputs and ask the model to learn the temporal dynamics. So this is our experimental setup. For training, we use around 1 million instruction videos on YouTube, and they cover a wide range of topics such as cooking, gardening, and even fixing cars. The particular data set we are using is called How to 100 Million. It was released by INRIA. And then we run off-the-shelf ASR system to get noisy speech annotations with timestamps. None of the training videos were manually annotated. For evaluation, we choose several standard academic benchmarks that are human annotated with clean labels. And it is worth noting that for evaluation, we don't need, our model doesn't need the audio tracks. It's a vision-only model. So once the model is trained, we first conduct some qualitative analysis. Here, we ask the model to perform the task of recipe illustration, each row corresponding to 4 steps of some written recipe. We ask the model to condition on the input text and predict the one missing video token at a time. We then visualize the video tokens using the keyframes that are nearest to the cluster centroids. We can see that the resulting video predictions are quite relevant and high quality. Because of the k-means clustering operation we did, the retrieved keyframes could come from different videos. However, they are nicely aligned with the text recipe in semantic space. We can imagine a future work would be to train a video generator with consistent occurrence over time from this retrieved or generated latent video features. Another qualitative experiment will be to see if video bird is able to generate realistic features. Here we are providing a bowl of cocoa powder and a bowl of egg and flour to the video bird model. We ask to retrieve the future tokens at different timestamps. We can see that for the bowl of cocoa powder, our model first predicts that it will be put into the oven, and then it might be turned into either a brownie or a cupcake. Similarly, for the bowl of egg and flour, it also generates reasonable predictions. And finally, we also conduct some quantitative analysis. We took a cooking video data set called YouTube2 and performed the so-called zero-shot classification task. Zero-shot here means that we do not know the categories beforehand and directly use video bird to predict the objects and actions conditioned on the video inputs. On the right, I'm showing the zero-shot classification accuracy as a function of pre-training data size. We can see that as more videos are used for training, the accuracy keeps going up. And given enough data, it even surpasses the fully supervised accuracy, which is trained using the training data split of the YouTube2 dataset and the known close vocabulary beforehand. More recently, in this CVPR, Arsha, our intern, also has a work on going beyond instruction videos. The high-level idea is that we use the co-occurrence of speech and scene descriptions in movie screenplays to learn text-only speech-to-action classifier that predicts actions from transcribed speech alone. We can then apply this model to speech in a large unlabeled set of videos to get weak labels for action recognition. It has achieved very promising performance, especially on the long-tail atomic visual action recognition. Now let's move on to the second example, where we aim at discovering object structures and use them for tracking and prediction. First, I guess most of you are familiar with this Johansen experiments in 1973. Although we are only provided with a set of moving dots, it's clear that we can recognize the actions performed by the two actors here. The question we're interested in is actually, can we go the other way around and discover these structure key points from actions in videos? You might be wondering why we don't use the standard supervised technique, which have been shown very powerful for key point detections, as shown on the left. But there are cases, for example, robot grasping on the right. It is unclear how to define the key points for of individual objects, for example, for the glove or even for the marker pen. And it is desirable for us to discover these key points purely in a data-driven or maybe a goal-driven manner. As the only available inputs here are video frames, let's first take a look at what might happen if we resort to an image reconstruction objective. Here, I'm showing a standard autoencoder where the inputs and outputs are both neural network. And the bottleneck is just a feature vector. We can all see that the bottleneck is not interpretable, and it can choose to input any information it wants to, such as appearance, motion, or even just memorizing the pixels directly. Alternatively, we can ask the encoder to predict key point locations in 2D coordinates. However, to make sure that these key points are indeed semantically meaningful, we need to add two constraints. First, we want to add a constraint that only key point information is stored in the bottleneck. No appearance, no motion. So we need to provide a reference from T0, which provides the appearance information about the objects and the background. Second, we need to make sure that the 2D coordinates are indeed interpreted as key points. For this purpose, we render the 2D coordinates as Gaussian blobs on the image and concatenate with the reference frame. We then use a deconvolution network to maintain the spatial locality. By restricting the bottleneck only contain 2D coordinates and reconstructing source frame from a reference frame, it encourages the model to detect key points that are invariant to viewpoint changes. We can also take one step further to train a recurrent neural network to predict how the coordinates might move to the future timestamps. Instead of reconstructing the frame at T1, we can then reconstructing the unseen future frames, and this is our framework. We can see that by generating the generating the future pixels, the key points are not only required to be invariant to viewpoint changes, but are also encouraged to have robust temporal dynamics, which can be captured by our RN model. And this basically allows us to train a generative model of video pixels with the desirable side effect of discovering object key points and their trackers. And this process is completely self-supervised or unsupervised. We can imagine that there are multiple possible futures given the same observed video frames. And to handle this, we use original RNN to achieve stochastic prediction of future dynamics. A recurrent neural network itself is deterministic, and it uses a fixed function to update hidden states H here. And here we can inject stochasticity by adding a latent variable Z. We can treat the latent variable as the latent intent representing the state of the mind of the agents. And during inference time, we can sample from the latent distribution so that the model can now generate diverse futures. Here are some qualitative results. We train and evaluate our model on the human Super6 dataset, which has different actors performing different actions before a fixed camera. The first row, I'm showing the ground truth, and with the observed video frames in green and predicted video frames in red. Second row, I'm showing the detected key points and their track list. And this final row shows the reconstructed frames, which are quite high quality. And we also show some of the tracking and predicting results in a quantitative analysis. Because there are multiple features, and for each baseline listed here, we run multiple samples and took the average. And the main observation we get here is that our performance shown in red curve is almost as good as the supervised version. And because our discovered sequence are optimized for temporal dynamics, for long horizon predictions, such as over 4 seconds ahead, our model even outperforms the supervised baseline. Here, I'm showing the video predicting results. Each column is a different sample. And first row is the ground truth, second row is previous stated art, third row is our method, and final row is without the structured architecture bottleneck. And we can see that by using a structured representation, modeling temporal dynamics in this structure space, our method is able to generate stable video predictions for a long time horizon. But the baseline methods tend to be more blurry when it comes to the faraway future. And another benefit of having a structured interpretable representation as our dynamics predicting bottleneck, that we can directly manipulate the key points and conduct condition generation, for example, by stretching different body parts. And we can see that by stretching the body parts corresponding to legs and arms, the corresponding generated results are indeed meaningful. And finally, we also apply our method on the DeepMind RL suite. Here are some of the action condition generation visualizations. Again, we can see that the structured generation approach is better than the unstructured approach. And what we use with this generation modeling is that we can use it for reward prediction. And which can be used to improve reinforcement learning policies. We can see that our structured model consistently uses lower error than the non-structured model. Okay, now we covered cross-model representation learning and object structure discovery. The final topic I want to briefly cover is the multi-agent behavior prediction. So the specific task we are interested in is vehicle behavior prediction, where the inputs are detected vehicle trajectories and scene contexts such as road maps. The outputs are possible trajectories for all vehicles in the next 5 or maybe 3 seconds. And this task is important for self-driving cars, apparently, for it to plan ahead and make the safest possible decisions. I like this task a lot because it perfectly complements the previous tasks, where in the previous tasks, the structures are to be discovered, and here the structures are given, but the model to make use of the structured information is missing. Most of the previous methods on this kind of behavior prediction adapt a non-structured representation on top of the high definition road maps. And they basically render these maps in a top-down view and into color-coded entities, such as maybe different color coding for different cars, pedestrian or traffic lights, as shown in the example below. And they then use a standard convolutional neural network to encode the rendered road maps. And clearly, there are several limitations with this approach. First, the ConvNets are not designed to capture long-range structures, which are important for behavior prediction if we want to plan 3 or 5 seconds ahead. And second, it is often unnatural to map structured metadata into maybe color-coded images. It might lead to missing information or some ambiguity. And finally, from an application perspective, all these steps of rendering and ConvNet encoding are computationally intensive. Now, let's look at what the structured information we have before we design the model architecture. So we can see that from an HD map, there are points such as maybe stop signs or other traffic signs. And there are polygons such as maybe crosswalks. And finally, there are curves such as the line boundaries. And it's worth noting that vehicle trajectories can also be treated as curves, but they have the timestamps associated with those vehicle trajectories. So all these elements can be approximated with polylines, which themselves are collections of vectors. And these vectors can be associated with 3D coordinates as property and optionally timestamps or other properties. And this motivates us to propose a vector net, which is a structured representation of the both same context and vehicle dynamics. The inputs to vector net are the polylines from both the high detailed maps and also the vehicle trajectories. Each polyline is represented by a collection of vectors, the polyline group ID, and this other state information, such as maybe whether it's a line boundary or a vehicle trajectory, or maybe the color of the traffic light at a certain time. And these inputs are then fed into a hierarchical graph neural network. In the first level of the hierarchical graph neural network, it's composed only of polyline subgraphs. It takes information within each polyline, such as maybe local road geometry and local vehicle dynamics, and encode them into subgraph features. And then in the second level, which we call global interaction graph, the vector net model exchanges information among all those polyline subgraphs. And the goal will be to allow global interaction to capture high-level maybe interaction models, such as how to follow the lanes even it's far away into the future, or maybe when to use other vehicles at their intersection. Our vector net is optimized with two training objectives. The first one is a standard target vehicle trajectory loss function, such as maybe you can use Uber loss between the front shoes and predicted future trajectories. We also add an observatory training objective, where we randomize out a subset of the node features in the global interaction graph and ask the model to complete the mask node features. The goal of this observatory loss is to encourage the vector net to capture useful relations between all elements in the graph. We apply vector net on two behavior prediction benchmarks. One is internal benchmark from Waymo, and the other is a public benchmark from Argo. We compare vector net with a ResNet 18 encoder applied on render maps. We can see that a vector net achieves lower displacement error while having significantly fewer flaws and parameter counts. For more comparisons and ablation studies, please refer to the paper, or we can talk using emails. And here are some visualizations. The purpose of this visualization is actually on the right, where we try to see what the vector net looks like when it tries to make the predictions. For this example, it's a lane change example. We can see the vector net uses a graph attention to attend to the source lane and the target lane of the lane changes. And you can also see that the attention stretch along across the image, which is hard for a convolutional neural network to capture due to its limited receptive field. And also the vector net is able to capture diverse relevant context information. This is an example at a traffic intersection. Although the vehicle decides to go straight, our graph attention actually enumerates all the possibilities, including turning left and turning right. Okay, now I have covered 3 topics on structured representation of the visual world. We can see that the structured representation are interpretable, such as providing visual linguistic correspondences. They are able to discover object structures. They are good at capturing non-local structure, temporal or cross-modal relations. And finally, it provides a natural inductive bias from multi-agent systems. I hope this talk has convinced you that learning structured representations is important, and it is needed for us to recognize high-level visual concepts. Thank you. And please let me know if you have questions, and please feel free to email me afterwards. Bye.
Okay, so one question which is from YouTube is, are there any experiments which show how the struct VRNN performs on multi-object and multi-class predictions?
Yeah, that's a great question. So I also replied on YouTube that it's not covered on in this paper. In this paper, we only considered human 3.6, which is a single person, and static camera, which is a little bit constrained case. And there's another paper, and also there are follow-up or related works on like modeling multi-person trajectories in sports videos. There we indeed cover multiple objects or multiple persons. Yeah.
Cool. And a question from Gyungin Shin. So says he's worried if detailed visual information is lost during video tokenization in VideoBERT. Do you think that that's a valid concern?
That's a great question, and that's indeed a valid concern. So what we observe is that when we transfer the representations to cooking videos, the quantization doesn't hurt much. Actually, it may even help by bringing robustness. But if we are trying to transfer to maybe slightly different domains or more fine-grained recognition tasks, this quantization is indeed harmful. So we have a follow-up paper called Contrastive Bidirectional Transformers. It's aiming to remove this tokenization step. And there are also many VisualBERT papers trying to learn representations without the quantization step. Yeah.
Cool. Okay. I also had a question. One of the graphs you have, which is nice, it shows this strong positive influence of having greater quantities of pre-training data. But if I understand correctly, without supervision, you're uniformly sampling. Is that correct?
Sorry, which work is that?
So I think it was VideoBERT or the cross-modal learning in a self-supervised model, so that you don't use any labels for the data originally. And I guess one of the challenges might be as you go to larger and larger quantities of data to get more gains, presumably the concepts you see in those videos are going to follow something like a power law. So you might see interesting stuff rarer and rarer. So do you have, or is there a mechanism in the model, or have you looked at ways that you might do some kind of, I guess it's kind of like a form of active learning where you use cues during training to try to skew the sampling towards interesting bits of data?
I think that's a great point. We haven't tried that, and it also depends, it's something worth trying. And I guess it also depends on the distribution of your validation set or downstream tasks. And also, I think you brought up a great point that many of those recent self-supervised learning frameworks, they work on human curated data sets like ImageNet, and it's unclear whether the observations will transfer to maybe real images in the wild. Yeah.
Cool. Thanks. Okay, I think that's all the questions on the chat. So thank you very much, Chen, for your talk. That was fantastic. And I'm not sure if we have like an applause thing.
Thank you.
And I guess with that, we will transition on to the next talk, which is from Shizhe Chen on fine-grained video text retrieval with hierarchical graph reasoning. And I believe Antoine will, again, slickly translation. Thank you.
Hi, I'm Shizhe from Renmin University of China, and I'm going to introduce our work, Fine-Grained Video Text Retrieval with Hierarchical Graph Reasoning. This work focuses on video text cross-modal retrieval, which is using sentences to retrieve desired video content. Compared with the traditional keyword-based search, the sentences contain richer and more structured details to express different user needs. In order to accurately retrieve videos, it's important to understand fine-grained semantics in the query sentence. The sentence naturally contains hierarchical structures. The overall sentence describes a global event. The event is composed of different actions, the main verbs in the temporal dimension, and each action consists of different entities as its arguments. For example, the noun phrase "an egg" is a patient of the action broken. Such structures benefit to understand fine-grained local components in the sentence, and how different components compose to the overall event. However, previous works mainly ignore the structures. The dominant approach, global matching, uses one global vector to represent video and text. It's hard for them to capture fine-grained details. Another method is local matching, which aligns each word with videos. it cannot express complex relationships among words. Therefore, in this work, we propose to take advantage of the hierarchical textual structures and match text and videos at both global and local levels to improve fine-grained cross-model retrieval. Our proposed hierarchical graph reasoning model consists of 3 modules: hierarchical texture encoding, hierarchical video encoding, and multi-level video-text matching. The core module is hierarchical texture encoding. We first decompose sentence into a semantic row graph. The red node is the event node, the green nodes are action nodes, and the yellow ones are entity nodes. The H denote different semantic roles that each node plays in the event. Then we initialize the graph nodes. We first use LSTM to obtain contextual word embeddings. The event node is a weighted average of word embeddings to focus on salient event. The local action and entity nodes are max pooling of their constituent words. In order to capture interactive context of different nodes, we use attention-based relational graph convolution network to encode the graph. We factorize the relational matrix to avoid overfitting due to multiple relationships. Finally, we obtain textual embeddings at 3 levels. Videos also contain multiple aspects, such as objects, actions, and events. However, it's challenging to directly pass videos as the text, which requires object detection, tracking, and action segmentation, and so on. So we explore a simple method to encode videos into corresponding 3 levels. We use different ways to encode video features for each level. The learning of the weights will be guided by different levels of text, so that they can focus on different aspects in the video. We fuse video and text matching at all levels. For the event level, we use cosine similarity in global matching. For the local action and entity level, we use attentive alignment in local matching. The model is trained using contrastive ranking laws. We evaluate models using MSR-VTT, TGIF, Vertex, and YouTube-to-text datasets. The evaluation metrics are recall at K, median rank, and mean rank. In the in-domain evaluation, our HGR model achieves consistent improvements on all datasets. We also carry out the ablation studies to evaluate the different components of the model. We can see that the graph attention and semantic role awareness are both important to hierarchical texture encoding. Using different video weights at each level for video encoding is also beneficial. We also conduct generalization evaluations. We first pre-train a model on the MSR-VTT dataset and then test it on YouTube-to-text dataset. The previous state-of-the-art model, dual encoding, though achieves better in-domain performance, it doesn't generalize well on the new dataset. Our HGR model achieves better retrieval performance in both in-domain evaluation and cross-dataset generalization. It shows the advantages of our hierarchical decomposition. To prove the ability of our model for fine-grained retrieval, we further propose a binary selection task. The task requires the model to select a sentence that better matches with a given video from 2 similar sentences. The positive sentence is the ground truth video description. The negative sentence is generated by perturbing the positive sentence, such as switching agent and patient of an action, or only keeping part of the information in the sentence. Our model achieves better performances in the fine-grained text discrimination task, especially for the incomplete events. Due to the fusion of hierarchical labels from global to local, our model can select the more comprehensive sentence. To conclude, in this work, we decompose video and text into event, action, and entity levels for fine-grained cross-model matching. It can perform better in in-domain cross-dataset and fine-grained selection evaluations. In the future, we'll improve video encoding with multiple modalities and fine-grained spatial temporal information. We have released the codes in the following link. Thanks for your attention.
Great, thanks for that, Shizhe. You can scan to see questions across various platforms, but in the meantime, I guess I will ask one. One thing that seems very nice about this way of structuring embedding is that you have this kind of hierarchical decomposition. So did you have a look at using it to cluster the videos along the attributes that you put into the hierarchy? Like, for example, if you just clustered on the action components of the embedding, were you able to get kind of nice semantic groupings of the videos where all the videos where everyone was doing one action were present and all the videos doing another action were grouped into a different cluster or anything along those lines?
We haven't carried out such experiments in our paper, but we can look at whether it can learn something through this semantic embeddings.
Okay, cool. I guess the experiments that you showed at the end with this binary task sort of hints that it's definitely able to do something along those lines, which is cool.
Yeah.
Okay, well then I guess if there are no other questions in the chat, then we will say thank you very much, Shizhe, for the presentation. And we will move on to the next one, which is ACBERT, Learning Global Local Video Text Representations from Linchao Zhu. And we will transition again back to Antoine for slide sharing.
Hi everyone, I'm Linchao Zhu. I am now presenting our paper, ACBERT, Learning Global Local Video Text Representations. We introduced ACBERT to learn joint video text representations from video text pairs in a self-supervised way. There are many existing models on learning self-supervised representations from images, videos, and texts. Recently, multimodal pre-training has been extensively studied for joint image text representation learning, and a few works has been focused on video text self-supervised pre-training, for example, How to 100 Million, VideoBERT, and more recently, like CBT and MU-NC. Instructional videos are a good source of data for joint video text representation learning. The instructions are available from automatic speech recognition. The videos are also from diverse domains, which are beneficial to learn from human daily activities. Miech et al. Introduced How to 100 Million for joint video text learning, and this simple ranking loss surprisingly works good for video text pre-training and achieved significant improvements on many downstreaming tasks. VideoBERT leverages BERT training for video text modeling. It discretizes visual features into visual words via clustering. The visual tokens can then be used for masked token prediction. However, these visual tokens lose detailed local information, and the interacting objects and human actions would be partially lost during clustering, which prevents the model from uncovering the fine-grained relations between videos and texts. To this end, we introduced ACBERT by decoupling verbs and nouns. We train a 3D ConvNet for verb classification, where verb labels is extracted from text descriptions. We also leverage pre-trained object detection models to extract local region features, and a prediction over local vocabulary is used as the label. The existing models usually take linguistic features and frame level or click level features for visual text joint modeling. In ACBERT, we leverage 3 sources of information for cross-model pre-training, which are action-related features, region features, and language embeddings. For example, visual features of string balls are usually helpful to predict token string ball when it is masked out. I will now introduce a new transformer structure for the encoding of 3 sources of information. The standard transformers usually take all inputs no matter what the modality the feature is. They treat visual features and text features equally. We introduced the Tangle transformer to encode each modality. The transformer weights are not shared. To further introduce more interactions between different modalities, we leverage 2 multi-head attention blocks among the transformers. The global action inputs are used as a query to attend linguistic inputs. The output will be combined with region inputs. The combined feature will be forwarded to the region transformer. Similarly, the global action will also attend region inputs. The outputs are combined with linguistic inputs and they will be forwarded to the word transformer. In this way, our Tango transformer utilizes a global cue to guide the selection of local hints from linguistic and visual features. Equipped with Tango transformer, I will now introduce the details of Egbert training. Here are two clips. The first clip is with description rotate shrimp balls. The second clip is with description add spinach. The stacked frames will be forwarded to a 3D ConvNet. The action features can then be obtained. The 3D ConvNet is pre-trained with the verb as the label, so the obtained features are action-related. Region features are extracted by a pre-trained object detection model. The action features and the region features are served as visual embeddings. We introduce two tokens for each of the features. The act feature represents that the input is about an action. The region token represents the input is a local region. There are also word tokens. For those word tokens, their visual embeddings are empty. The segment embedding is introduced to distinguish the two segments. For example, there are two segments, and S sub A and S sub B are introduced. The position embedding is introduced to record the order of the inputs. We have introduced all the input modules, and now we introduce 4 tasks for Egbert training. The first is the masked language modeling. Similar to bird training, the word shrimp is masked out. The goal is to predict the masked word shrimp. The second task is masked action classification. For example, the rotate clip is masked out, and the Egbert is trained to predict the masked action. The third task is masked object classification. For example, the region of spinach is masked out. The Egbert is trained to generate the masked non-prediction. The final task is cross-model matching. This task checks if the visual and text descriptions are matched. We pre-train our model on how to 100 million, and we evaluate the pre-trained model on 5 downstream tasks. We evaluate video captioning on YouCook2. We outperform VideoBird by 1.7 on Meteor score. We evaluate action segmentation on the coin dataset and achieved 22% improvement. We also evaluate on text video clip retrieval, and we outperformed the text video joint embedding model trained on how to 100 million by 5.4 on YouCook2. The results on 5 downstream tasks demonstrate the effectiveness of our model. More results can be found in our paper. Thank you.
Great, thank you for that talk. We can have a skim to the various threads to see if there's any comments. I guess one question I would have, having looked at the core ideas, it seems like the action features are really playing a very critical role in this framework in providing the kind of the inputs to the transformer. Do you have a sense of so are these action features that pre-trained on kinetics? Was that right?
These actions, thanks Sammy for asking. These action features are pre-trained on kinetics and then fine-tuned on the how to 1 million dataset.
Okay, cool. And do you have a sense of, I guess it's kind of computationally expensive to run these experiments, of how changing that pre-trained representation would have an effect on the overall framework?
So the verb label is retrained on the how to 100 million. So I mean, the final classification is replaced with a new vocabulary. Yes, it is very expensive. We use 4 V100 with 32 gigabyte GPU, and it takes more than a week to train a few epochs on how to 100 million.
Okay, cool. One other thing that I noticed is very interesting, you had these 4 different losses to encourage the model to learn. And if I understood correctly, 2 of them, one was predicting the region from the other cues and predicting the action from the other cues. So, and it seems like the experimental results show that it's generalizing incredibly well. I guess, do you think intuitively there might be some challenges for generalization if you did if you were to say predict the action from the objects, in the sense that maybe there's a difficulty in generalizing to novel combinations of actions and objects if the model is explicitly encouraged to predict actions from the objects it sees in the training set? Or do you think maybe that's not really a challenge?
Yeah, it is challenge, but from the current setting, for example, the shrink ball is masked out, so the object is masked out. The object reading features is masked out. The action features can be helpful to predict the label. As you mentioned, that if we mask out the action features, but those visual features, for example, rotate shrink ball features, I think it can be helpful because those text region and action features are correlated.
Okay, cool. Thank you.
Thank you, Samuel.
Then I guess if there are no other questions, then we will transition on to the next talk and say thank you very much to Linchao. Next talk is Visual Grounding in Video for Unsupervised Word Translation by Jean-Baptiste Alayrac.
Okay, thanks, Samuel. So hi everyone, I'm Jean-Baptiste Alayrac, a research scientist at DeepMind, and today I'm going to present our work, Visual Grounding in Video for Unsupervised Word Translation. And the question we ask ourselves in this work is, how can we learn a link between different languages from unpaired narrated videos? And just to illustrate a bit our motivation, let me start with this simple example. So imagine that you are a bilingual children where your parents are from different nationalities. For example, your father might be English and your mother might be French. One day you might cook with your father that will tell you, I need to mix the eggs with the flour. And this is the kind of visual scene that you will see. On another day, you might cook with your mother, maybe in a different kitchen, a different scene, and she will tell you, je casse les œufs, which means I break the eggs in English. And what we argue in this work is that thanks to the visual common ground between those two scenes, this helps children to learn relations between languages and to understand that the word eggs means œuf in French. So similarly, we will be placing ourselves in a similar setup where we'll be given a set of narrated videos in English and a different set of videos narrated in another language, such as French. So to do that, we are going to build upon the how to learn dataset that was used in the previous talk. So this dataset contains lots of clips, 100 million clips, where narrations have been transcribed into text using automatic speech recognition. However, this dataset was sourced from English videos, so that we extended it to different languages, including French, Korean, and Japanese, to be able to perform this work. So now I'll just present our model, which is really simple. So it will alternate between sampling videos in English with their corresponding narration. And then what we are going to do is to process the narration with first extracting word embeddings and then projecting this collection of word embeddings into a single vector using this two-layer network. For the video, we are going to extract a representation that we will also embed into a single vector of the same dimension as the text embedding. Then we are going to use a contrastive loss, which is described in our Mill and C paper that we will also present on Thursday during the conference. And the intuition behind this loss is that it will try to have corresponding narration and video embeddings to be close to each other in the space, whereas others should be far apart. The difference here is that we are going to also sample videos narrated in another language. For that, we are also going to extract word embeddings in French, and then we are going to process those word embeddings with a learnable adapt layer, which role will be to emulate as much as possible the embeddings of the other language, so that they can be processed with the same neural network. Finally, we use the same contrastive loss to map these French embeddings together, close together with the videos. By doing so, we are going to learn a bilingual visual joint space where we are going to be able to input both English, French, and video as inputs. So next, to evaluate the quality of the joint bilingual space with, for example, English to French word retrieval, what we are going to do is, given a simple word in English, we can score all French words using dot products in that space in the dictionary, and then we can compute the percentage of the time that the correct translation is retrieved in top 1, for example. So if we do that on 2 different data sets, we observe that this method, this Bayes model that I just presented, enables to learn good translation of words. And this is even more true when going for words that are more visual, because we can simply look at the performance on visual words where we remove abstract words. But the most interesting question is, do we really need vision at all? Do we need those videos to learn from? In particular, a very interesting result that has been shown in the language literature is that one can align word embeddings in different languages via a very simple transformation, such as rotation of the space. And for that, only a few correspondences between the 2 spaces are actually required to correctly estimate this transformation. And in particular, people have tried to come up with unsupervised approaches that do not require any language paired data to learn that alignment. And here, the question we are going to ask ourselves is, since this method suffers from some robustness issues to different problems, can we use vision to improve those methods? So for that, let me first explain you quickly how one of these methods called Muse works. So it works in 3 stages. During the first stage, an initial linear mapping between the 2 word embeddings is found using an adversarial approach. Then using this initialization, some anchors can be found, promising anchors, that are used to refine the mapping using the Procrustes algorithm. Then once this is done, the mapping between the 2 words are further refined using a normalization using local neighborhoods. Our proposed Muse algorithm is a simple modification of this algorithm, where we just observe that the adapt layer that we learn during training the Bayes model can actually serve as a good initial linear mapping for the algorithm. So we simply replace the first step of the Muse algorithm by using this adapt layer, and this defines the Muse method. So what we show here is that by using this kind of prior knowledge from the language, we are going to improve a lot on the Bayes model that was not using these techniques from the language domain. But more interestingly, we can show that we are actually able to improve over the methods that only uses text to perform word translation. And this is even more true when going for more different language pairs, such as English and Korean or English and Japanese. In this slide, we also look at another problem of text-only methods, that is that they are really sensitive to the fact that the initial word embeddings that you use to align should be trained on similar training corpora statistic. So what I'm showing here is the results when we take word embeddings from how to learn them in English and word embeddings from how to learn them in French. So if we do so, all methods kind of perform the same, even though the Muse method that is using vision is a bit better. But then now, if we start training the word embeddings on different corpora that have very different statistics from these instructional videos, such as WMT or Wikipedia, the methods that only uses text performs really bad, whereas our method is able to significantly outperform this method. So now let me just conclude and give you some potential future work. So first, I've shown that unsupervised word translations through visual grounding is possible. And more importantly, I've shown that the information contained in vision is actually complementary to the one contained in the structure of the languages, which enables us to have a better and more robust approach for unsupervised word translation. As future work, we plan to go from words to sentences, But also we think it's interesting to consider such multilingual data sets to learn better representation, because you can have larger data set and also being less biased towards only training with English. And we will have our Q&A on Thursday. So if you're interested, don't hesitate to come there and ask us questions. Thanks a lot.
Fantastic. Thanks a lot for that talk, Jean-Baptiste. I can skim to check any questions we had coming through. I have one comment, which was, if I understand correctly, you're learning this joint space with multiple languages concurrently. So they're all sharing these parameters. What effect does that have on the model? Does it work as some kind of magical regularization, or does it strongly hurt the performance of the model on retrieval, let's say, if you were to just constrain at test time to one individual case?
So you mean retrieval, like text to video retrieval, for example?
Yeah,
or?
yeah. So you train with these multilingual data sets, so then you just go back into one at the end. Is there a benefit, like there has been in kind of translation, to having all of these shared data?
Yeah, so actually the issue is that if you don't share at all, like, yeah, so we won't have this adapt layer that is learned. And I think we have some ablation in the paper that do that. But regarding the video, I think it can just improve the quality of the video representation, because you get just more training data. So it's really important to share this vision network across the different languages. So there, I think it's actually beneficial to do this sharing.
Cool. One other thing I noticed was that the text encoder looks very simple compared to what we're seeing in a lot of other settings. Do you have some, is that something you found through ablation, or you just found that it worked very well, or what was the kind of intuition?
Yeah, so actually, like this model comes from our How to One of Them work with Antoine and others. And then during our paper for Mill and C that you might have heard about, which will be presented on Thursday, we've actually ablated different language models, where here, like, the task is really to learn visual representation. So we start completely from scratch. And there we've observed that this simple model, which is almost just a bag of words when we think about it, is just a collection of word embeddings that we then max pool together into a single vector. This was actually performing well in our downstream task, performing better than more advanced language models, such as recurrent neural networks, or we've tried transformer as well. And I mean, for me, it's still a kind of, open problem to see how we can improve this. And we have different hypotheses. One is that maybe the downstream tasks we consider, which are just, text to video retrieval, are maybe simple enough so that you don't really need to have a complex language understanding, that you can just spot words, for example. But yeah, this is still ongoing work. And I mean, it's a great question, basically, because I don't have a good answer.
Okay. So I don't see any other questions. So I think we'll end it there. Thank you very much for doing that talk. That was fantastic. Thanks.
Thank you so much.
Our next speaker is Carl Vondrick from Columbia University, and it's a great pleasure for us to have him with us today. And he will be talking, as we can see, about learning from unlabeled video. Okay, thanks, Carl.
Okay, thanks so much for organizing the workshop and inviting me. Yeah, so today I'm going to talk about some of the work we've been doing and trying to learn from video. Oh, how do I go? Okay. So computer vision really has made a lot of progress in the last few years on building models for doing action understanding in video across really unconstrained situations. What we've been noticing as we're kind of crawling through the data is that there's often a bias for success in most of these data sets for video. People, when they shoot the basket, they always make the basket, right? People are on unicycles, going down a rocky mountain, right? People are kayaking off a waterfall and they survive, right? And this is really nothing like my life, right? Hopefully this is nothing like your life as well, right? I'm always failing. I'm always stumbling at my action. I never actually achieve my goal. this is what my life is really like, and this is not what are the types of videos that we have, right? That we often study and envision. So we're very much inspired by how people, as well as other animals, are actually quite good at inferring that, you know, maybe this action was not intentional. Maybe someone didn't intend to perform this action. Maybe this action did not let them accomplish their goal. And there's been some really fantastic work out of the Max Planck Institute by Felix Warneken, who studied both young children as well as some monkeys, to show that, you know, from a very young age, right, there's this ability to actually recognize when action is no longer intentional, and even predict what the goal is. What was the goal that the person wanted to perform? So here's an example, right, where the experimenter, right, is struggling to grab this object, and the monkey is able to infer this, right, and actually predict, well, what was the goal? What, you know, maybe this wasn't intentional, and actually go and try to help out. So I think there's this question when we talk about understanding human action, right? It's not just about trying to classify the actions into different categories, but can we try to organize action into what are the intentions? What is this intentional, right? What is the goal? Is this an obstacle, or is this something that helps? So we've collected this new data set, which we've just released, and this will be appearing as a poster tomorrow at CVPR. It's called the OOPS data set. And this is just a large collection of videos, about 20,000 videos that show action across these different situations that's unintentional. So it's basically a big data set of people kind of messing up at their action. And so it covers various different scenes. There's you know, kind of, there's both videos of a single actor kind of making a mistake in isolation. There's multi-agent, and there's two people making a mistake, as well as interaction with humans and animals. We download most of these videos essentially from YouTube, just by finding these so-called fail videos online. I think it's just a really cool data set of you know, things going wrong. And one thing as you venture into these questions of intentionality, if you go too deep down the rabbit hole, it becomes very subtle and really hard to figure out, well, was this intentional? Maybe this was just someone pretending that this was intentional. And so you get kind of into this deep rabbit hole. What I like about this data set is that all the videos here are, it's very obvious what the intention was. And it's kind of, when we annotate this data set, all the annotators agree on whether this action is intentional or not. And so I think this is a really good first step for the vision community to try to explore these issues in an unconstrained domain. Because this is something that humans agree on quite a lot. So we should be able to at least make some neural net or some machine learning model, right? Try to figure out the intentionality here. And I really just want to emphasize just the breadth here, right? This is really unconstrained. It has all different types of camera views, all different types of activities, all different types of objects and people. And so I think it's going to really be a challenging benchmark. Okay, so this data was collected by two students in our lab, Dave and Bo. You can see them top right here. And you can check out more of the data set and download all these videos at oops.cs.columbia.edu. Okay. So the data set, you know, we're an academic lab, so this isn't you know, some massive, you know, data set of millions of videos that we able, but I still think it's pretty large. It's about 20,000 videos. They're on an order of about 10 seconds long. So this is actually very nice for this current state of the art in trying to do video understanding. You don't have to process this 2-hour movie to figure out whether something was intentional or not. Right? These are very atomic actions, right? These are actions that are unintentional, just in an order of 10 seconds. And they cover all different types of actions and scenes. So on the bottom left and the bottom right here, we show a plot, a histogram, just trying to show off the long tail distribution of the different types of action categories and scene classes that are covered in this data set. Okay, so the data set here that we've collected and released now online, you can go experiment with this, is we've annotated the videos into the temporal position of the video that the action switches from intentional to unintentional. So all the videos start out intentional, and at some point they're going to switch to being unintentional. And so we annotate that point. We annotate it three times in order to make sure that humans agree. And people do tend to agree on this task. And so then the problem we're going to pose in this work is, can we actually predict when the action switches to unintentional, right? And we try to do that type of segmentation problem. Can we segment the video into when it switches to being unintentional? We're very interested in trying to do this from just self-supervision. So even though we have to annotate some videos for evaluation, is it possible for us to learn to do this task without requiring huge amounts of labels? We think this might be possible because there's evidence that in children as well as some animals are able to perform this task, right? And so it seems like we should be able to learn this from a limited amount of supervision. And so what we've been investigating is how can we use unlabeled video to learn this representation for intentional action? Can we learn a representation that's able to predict whether something's intentional or not? And so we have a huge set of videos, right? As the other speakers in this workshop have done a great job at talking about, right? There's tons of videos that we can get that are just going to show off the realistic diversity of our world, right? They cover all different types of dynamics, and we want to try to leverage this collection in order to figure out, well, what is action that's intentional, what is action that is not. So we investigated a few different perceptual clues that we could learn, that we could use as a way to learn a representation for intentional action. The first clue that we looked at is predictability. This is now pretty standard in self-supervised learning. This is looking at how predictable is the future. So perhaps action that is unintentional is hard to predict. And so this might be one clue to try to figure out whether something's intentional or not, right? Is this a deviation from expectation? A second clue might be temporal order, right? Do you have to fail before you succeed, right? Is there some clue in the order of the frames? And this also has been explored quite a lot in the community as a way to learn a representation for video. The one clue that we also looked at that actually worked the best, and actually I think it's pretty interesting, a self-supervised clue, is we looked at the speed of the video as a way to learn a feature for motion. And so as far as we know, this was a new clue for self-supervised learning at the time when we submitted the paper. There's now, even at this conference at CVPR, there's at least 2 other papers that also look at the speed of the video as a clue for learning representations. So the idea here is that the frame rate of the video is intrinsic to the modality. And so because it's intrinsic, it's basically a free label for us. And we're able to manipulate the speed. It's very easy for us to synthetically change the playback speed of a video. And so because we're able to perturb this, what we can do is we can create a self-supervised learning problem where you take your favorite architecture for video and you train it to try to recover what was the original frame rate, right? So how much time has passed inside this video? And the hypothesis is that this should actually learn very good features about motion, right? For us to understand that this video, you see here, has been slowed down, right? We have to understand about the dynamics or learn some patterns about the dynamics of water and how people move through the scene, right? And this is how we can tell that this video, the frame rate in this video has been changed. So I think this is actually a very interesting clue for learning representations of dynamics, because this is basically available in all videos, right? The rate at which the video plays is something that is available in each video. Okay, so one of the things that it's actually what's interesting about this is that the speed at which we watch video actually impacts how you interpret intentionality. And so there is a well-known court case, I think this was about 10 years ago in the United States, where the jury had seen a surveillance video that was slowed down. And what happened was that by slowing the video down, it made the crime look intentional, right? When the crime actually may have not been intentional, right? But because it was slowed down, it created this illusion that you have time to premeditate the action. And so this actually this actually might be a cool clue for learning representations of intentionality. And there's a lot of fake news campaigns right now that you've probably seen, where the speed of the sound or speed of the motion is changed, which in order to create an effect, whether someone's drunk or something like that, right? So the rate at which time ticks, right, has a big influence on our perception of the world, and perhaps it's actually a really good clue for self-supervised learning too. Okay, so we can train this model up on large amounts of video that you can download. It could be from YouTube or any type of video collection that you have. I think we trained this on the kinetics data set, but we didn't use the labels. We just used the videos. Okay, and so after you train this, you get this feature space that you can use for a couple of different tasks, right? You get this feature space inside the convolutional net, which we can transfer to some downstream tasks. One thing that's pretty cool is that if you look at this representation that's learned and you look at the nearest neighbors in this space, the distances tend to be meaningful and cluster based off of objects that have similar motion. So here's a few examples that we found, right? On the very top, we even put this image of a bird. The nearest neighbors are going to be of other videos of animals, right? And same for sports, right? So these are all motions. These are all activities that have very similar motions, which suggesting this model is starting to learn some features about motion. So going back to a task that we started with, which was trying to classify whether this action is intentional or not. What we're going to do is we're just going to first train the model to get these features. It's a 3D CNN, and then we're going to fit a linear classifier on top of this feature space with a little bit of labeled data in order to classify whether action is intentional or not. So we need a little bit of labeled data to say whether this is intentional or there's some sign ambiguity, and we use the labeled data to fit that classifier. Okay, so here's a couple of examples of the results. So here's a video that's playing. On the very bottom, you can see the predictions from the model as the video plays. So the ground truth, the point that the human annotators have marked, is the dashed line, right? The vertical line. That's the point that the annotators marked, is where the action switches from intentional to unintentional. And the model is making 3 different predictions, right? It's predicting whether it's intentional, whether it's in a transition period, so whether it's both, or whether it's unintentional. Okay, so here's another example. This is the multi-agent dynamics. This one tends to be, this one's a little easier for the model. I think it does, you know, I don't think we've solved this problem. We're still actually quite far from human performance on this data set, but I think it's interesting to see what this has learned. It sometimes gets the predictions right for the wrong reason. Here's an example that I like a lot, where it gets this right at the very end, that this action is unintentional. Like, no one ever wants this gate to come down and hit them on their head, right? This is kind of common sense to us. We would never want, you know, to do this, right? And it seems like the way that the model should be learning to solve this problem is by doing something with theory mind, right? You really would want something with theory mind here, where the model should be ideally it should be recognizing, oh, the person doesn't see the gate, and that's why this is unintentional, right? I don't think the model's doing that, right? I don't think just learning by predicting the speed of the video is able to learn such a complex function. But I think this is an interesting problem because this is a task where you might need this type of reasoning, where you try to follow the gaze and understand what are the goals behind people's actions. Okay, so the last plot here is what we're doing is we're comparing the performance of the model against some of the videos breaking the data set down by the types of unintentional action in the data set. So on the vertical axis here, what we're showing are each of the videos in the diagnostic set are annotated with what caused the unintentional action, right? Was this something in the environment? Was this because the person didn't have enough skill? Was this because of limited visibility? And what this is showing is how the performance of this model changes as a function of these different complexities. And so our model is in red. So yeah, the zoom windows. Yeah. So our model is in red. Lower is better here. So our model is self-supervised. It's in red. If you pre-train with kinetics labels, so if you have access to the labels to the task, what you get is in gray. So of course, this is the same old story in self-supervision that having labels actually helps the task, right? So you do improve with some annotations here. And then human performance, we had everyone in the lab come in and do this task as well. Human performance is this dashed line. And so you can see there's actually quite a long ways to go, right, before we're able to approach human performance, even on this very simple task, right? We designed this task so that it's pretty easy for humans, right? And there's still quite a gap here. It's not, humans are not on at zero error, right? So it's still a hard task, but they're actually much better than the state of the art right now. Okay, so you can check out this paper more at oops.cs.columbia.edu, or come by our poster tomorrow, poster 993 at 10 a.m. Seattle time. So, I didn't want to do that. Here we go. Okay, so in the last 10 minutes here, I want to talk about another work where you're trying to use unlabeled video to learn representations. And here what we're trying to do is we're trying to leverage the synchronization between vision and speech in order to learn, try to learn a representation in vision, but also learn a representation in language. And so this is kind of like what we do all the time when we travel to a new country, right? When you travel to a new country, you don't know the language. And we saw just before me, right? There was a great talk from DeepMind about trying to do translation where vision is kind of a common ground. It's actually really amazing the type of process that goes on for us to acquire language, right? Especially when you go to new country, or trying to figure out and trying to infer what are the meanings of all these words. So here's a video I'm going to play.
And now here's what we're going to go in with the actual Aki that I rinsed off earlier.
So there's this new word, at least this was a new word for me. I don't know if everyone else has heard of this, but there's this new word, Aki, right? And what does this word mean, right? And you're able to figure this out, right? You're able to actually infer quite a lot about this new word by opening your eyes, right? And actually able to see the scene, right? So you can probably figure out that Aki seems to be a food, right? It's probably this white yellow thing, right? So you can wash it probably, right? It's sticky, it's largely a cherry tomato. And so there's this very complex process that we had to go on. I think in your head, if you actually break down, what is the process you had to do to figure out what Aki means, right? Was it really just a simple correlation, right? Was there just some correlation between vision and text that you had to find in order to figure out what this word means? Or would you have to do some more complex reasoning, right? You have to figure out, well, to figure out that this is washable, right? You had to associate it with the word rinse, right? Because the speaker said that you could rinse it, right? That's how you know you could wash it. You know something about size because in relation to the scene here, right? You know what cherry tomatoes are, right? And so therefore you can figure out what the size of Aki might be. Okay, so we're really interested in this kind of analogy of the world traveler, right? As you travel around the world and you have these new words that are coming in, how can you figure out, right, what these words mean? So the state of the art and the work we heard from Chen in the morning is a great example of this. Is basically taking advantage of what's going on in NLP with transformers, where instead of just inputting a sentence into the model, you also input an image, and you train it on the same task as an NLP, which is a closed toast task, which is try to predict. You mask out a word and train it to predict what the missing word is. This is, you know, attaining state of the art across different vision and language tasks now. So what we're interested in doing is going a little bit step further. Rather than trying to learn what a word means, rather than trying to learn what stir means, what we want to do is we want to learn how to learn words, right? So we want to learn, you know, how, if you go to a new environment and you hear a new word, right? How can you learn what that means, right? Beyond just learning what this correlation is, right? How can you actually learn what that word means? Can we learn a policy that lets us acquire words? So we're going to cast this as a meta-learning problem. And this is an area that has really boomed in the last few years. There's kind of too much related work for us to put on a slide. And so we're going to cast language acquisition as a meta-learning task. And so the way meta-learning typically works is rather than us feeding in a single example into the model, right? What we're going to do is we're going to create a model of the learning algorithm and feed in an entire data set into the model, right? So it's not just going to be a vision text pair, right? We're going to feed in a set of vision text pairs into the model and learn it and basically train a policy to acquire words from that set. So at the very bottom here is an example of one very simple episode, right? There could be this test example, and you want to fill in that mass word. And what we want the model to do is to fill in that mass word by looking at the other examples in the training set, right? And trying to extract something from the training set so they can fill in the mass word. So the next question is, okay, how do we prioritize this agent that does learning, right? What is the model we want to use for learning to learn here? So the idea here is actually quite simple, simple, but I think it's actually very powerful, is that we can view transformers as a way of doing meta-learning. So because the way transformers work, they're not sequential. Actually, you can use them to feed in an entire set of examples. You don't have to feed in just a single example. And what the transformer is going to do is when you feed in the entire data set, right? You feed in an entire episode into the model. The transformer is able to extract these very complex parallelized relationships between elements in the episode. And so we think we can use this for meta-learning, right? It's we're able to feed in an episode and train it to learn, right, from this episode. So the specific task that we're going to do here, what we want to do is fill in the blank task, is you want to fill in what is this H02, right? What is that word supposed to be? What we're going to train it to do is to point to other examples in the episode. And that's how it's going to fill in the mass word. Okay, so I think one thing that's interesting about this is that we can be very explicit in how we construct these episodes. We don't have to create random episodes. We can create episodes specifically for the types of policies that we want to create. So And so what's interesting here is rather than us trying to hand design, right, an algorithm to learn here, we can just create examples that demonstrate how the model should learn, and let gradient descent do all the work to try to figure out what that learning algorithm should be. So in this work, we consider two different types of episodes. In the first type of episodes, there's always one or more new words. And so here in this top line is showing one of these episodes, and in this example, the word chair would be new. The model's never seen the word chair before. By training it to perform this task, by training the transformer model to take in this episode and point to it, we think it's going to learn a policy for word acquisition. We can also we also create other types of episodes. So another type of episode that we consider is for compositions. So here we're going to have, all the words are going to be familiar to the model, but it's never going to see some pairs together. So in this example, the model has never seen the phrase stir paneer, right? It's seen stir pasta and it's seen cut paneer, but it's never seen stir paneer. So this is the type of generalization that we want the model to do, and so we can actually train the model explicitly for this type of generalization. Now, instead of pointing to one word, it has to point to two words. Right? Okay, so one thing that's interesting about this model is that after you train this up, after you train this whole model up on any type of vision text data set that you want, you get this model that has two different modes. And you kind of get these both modes for free. One mode is just your standard language modeling task, where at test time, you only feed in a single example. And then what it's going to do is it's going to produce a representation for that example. And then the second mode is a word acquisition mode, where at test time, you feed in not just one example, but you feed in other examples that might contain new words that you want to acquire. Right? And so we can evaluate both different modes. So if you look at the very first mode, just on the language modeling, we evaluated this on a couple of different data sets. We're going to show you the most challenging one here, which is on Epic Kitchens. And so what we're comparing here is how well the model does at filling in the mass word versus whether the composition has been seen or not. And so the baselines here, which is both just BERT off the shelf, or we take one of these models for BERT plus vision, are shown in these first two columns. And what you should see is what makes a lot of sense is that for new compositions, there's a performance drop, right? There's about an 18% performance drop when the compositions are new. And this makes sense. There's no data to support that this composition should exist, even though language is a compositional space, right? So if you take our model instead, right, and you evaluate on the same task, right? So what I think was very interesting is that this drop is much smaller, right? There's only an 11% drop. Now, the whole model has actually improved. So even for the seen compositions, you have a performance gain. But I think what's really interesting here is that you get more robust generalization, right? When you go outside of the training set, right, there's a much smaller performance drop. Okay, I got to finish up in the last 2 minutes here. Okay, and so we can also evaluate the second mode here, which is on the word acquisition, where we give it a episode, and we test it how well can it acquire new words. And so here's an example of episode where the first 3 are in the training set of this episode, and the last one is a testing example. There's 2 new words here, right? There's avocado and skin. Both these words are new to the model. We withheld them at training time, and now in testing time, we're going to show them the new words. And so we can test the model, right? Which words does it point to? Well, it actually points to the right word, right? It's actually able to pick up, right, and what that word is, and use it to describe a new scene. Here's another example. There's cupboard and oven. Those are new words. And if you train it on this close task, right, it actually points to the right word. All right, so we evaluate this on a couple of different data sets, both Epic Kitchens and Flickr 30K. I mean, the conclusion is that we beat the baselines on this task. And what this chart is showing is the performance of the model on the vertical axis versus the ratio of the number of new words versus familiar words, right? So as this ratio increases, the problem gets more and more challenging because there's more new words that you've not seen, right? But for all points on this plot, right, the model's meta-learned is actually more robust. Okay, I think this is the last slide. And so we also tried to analyze what type of process this model learns. And so the way we did this was we took this transformer and we cut out different connections in the model, and we saw how much the performance drops. So if the performance drops a lot, then we can say, well, that connection probably is important. And so what this plot is showing is what connections are the most important, right? And so what this is showing is how information is flowing through this model, right? We can view transformers as a meta learner, and it's showing how information goes between different nodes, right? And so in the very left here, in the first layer of the transformer, what's going on is information is flowing from the text nodes, right, to the image nodes. In layer 2, they get kind of mixed up. And then layer 3 or 4, it goes back from the text nodes to the image node. So I think what's interesting about this is that this is learned, right? It is learn this basically from scratch. Okay, so I got to finish up here. So all of our code and data is online, expert.cs.columbia.edu. Thank you very much. Happy to take any questions.
Fantastic. Thank you so much, Carl. That was a wonderful talk. There are a few questions I'll read out from the chat. I guess that's the simplest way to do it. So one from Mardi Kalaya. Thanks, Carl, for the very interesting talk. In your opinion, how is intentionality different from the outlier detection problem if you define it within a given class?
Right.
I have a hard time distinguishing them from each other.
Yes, that's a great question. So the problems are different. So for example, if you're walking on ice and you slip, that might not be an outlier because that's pretty common. Most people are going to slip on ice, right? But it's still unintentional. This is one difference between the two problems.
Okay, cool. And then another question from Antoine, which was, it seems from the qualitative results that the unintentional part of the video is always at the end. Did you notice that kind of bias in general?
Yes, absolutely. So we do compare against that type of bias. So we plot that here. So in the middle here in B is showing where in the video the action switches from intentional to unintentional. So of course there's kind of a center bias here, right? In the center of the video, if you had to ignore the video and make a blind guess, you should probably pick this point here, right? So we compare against that, and the model outperforms it. There's a even stronger baseline that we considered I didn't talk about, but which we also outperform, which is we compute the flow of the video and we compute a histogram from that. And so we try to just look at just a simple kind of flow histogram, let you solve this task, and it does better than the simple fixed prior here, but it's still worse than one of our models.
Cool. One thing you mentioned in the talk was that maybe ultimately you have this hope that it kind of learns a sort of theory of mind. And one thing that comes across from the clips is that they're often quite funny. Do you think that the model learns some approximation to humor? Because I guess that's a skew that's present in the clips in terms of what people would be likely to upload. If you ran it on, say, like a slapstick actor running around on stage, would it predict lots of unintentional events?
Yeah, that's a great question. I think humor is pretty interesting. I mean, yeah, this model could be trying to predict something that is, maybe it learned some prior about what funny is. This is always one problem with data sets, right? Is that there's some collection bias. So the videos that we have, they were uploaded because they were funny. So we're ignoring all the other examples where it's unintentional action, where it's not funny, right? And this is definitely a bias in the data set. But I think it's true of most vision data set biases. I mean, I think the advantage of the data set, what I really like about the data set is how obvious the unintentional action is. I think, you know, if we're not ready, the field is not ready to go to, you know, 2-hour films and try to figure out, you know, did the bad guy really mean to do that over the 2 hours, right? That's too hard right now. So I think this is going to be a baby step towards that.
Okay, awesome. Thank you so much for the talk. I guess if anyone has any further questions, we can forward them by email and we'll move on to the next stage. Thanks again, Carl. So next we're on to actually the results of the challenge, which will be presented by Antoine. So we can attempt another slick transition.
Okay, so do you see my screen?
Yeah. We do.
Okay. So I guess that's the moment that you are all waiting for. So the challenge result and the talk of the top participant. So if you are just joining the workshop, so I'm going to summarize a bit the philosophy behind this challenge. So basically, it's a text to video retrieval challenge on 5 different datasets. So you have MSRVTT, MSVD, UCook2, ActivityNet, and DDemo. So these datasets, they are all video datasets which come with descriptions so that you can actually have a way to evaluate text to video retrieval I mean, with different metrics such as recall at 1, recall at 5, recall at 10, and median rank. And one particularity of the challenge is that so we provide video representations for each of these datasets, so that we put the emphasis on several things. So first, we can actually like put the emphasis more on the training objective rather than just visual representation, or also like the aggregation of the video features temporarily or just across like audio, motion, or appearance, for instance. But also importantly, also the language model, which plays an important role in the text part. And finally, it's interesting because as we provide the features, so I mean, it means that the participating to the challenge do not require having a large cluster of GPU. I mean, it surely can help to run a lot of parallel experiment, but I mean that's not. I mean, it can be easily. I mean, you can easily participate to such a challenge with only 1 GPU because like most of the computation has been done. So which means that it's accessible to most of the like academics research groups. And so in terms of statistics, so we had in total 10 different teams with a total of 38 submissions in the validation set. And so this is the evolution of the top leaderboard validation score full time. So you can see that so the challenge ran from April to beginning of June. And you can see, I mean, as most of the challenge in machine learning, that like the top score suddenly go really at the end, where actually people they put most of their effort at the last moment. And so in terms of results, so actually the results are already online. So but here, so these are the top 3 teams from that you can see actually also on the CodaLab platform. So at the 3rd place we have so the first author is Kaixu Cui from Xinhua Chuyuan. And then the second is actually Shizhe Chen, that was actually a presenter of the workshop. I mean the first spotlight, and actually the method that she proposed was actually based on the paper. And then the first place is from a collaboration between INRIA and Google with Valentin Gabeur as a first author and also as a presenter. And so a technical report is available for each team on the website if you are interested. And now we'll be following the talk of the presenter, and we'll start with first Valentin Gabeur, the first place, and congratulations to them.
Okay, great. So my name is Valentin Gabeur, and I'll present you our approach for the video Pentathlon challenge. So first, I'd like to thank the organizers of the workshop for this amazing challenge and for the invitation. So the work I'm going to present is a collaboration between Chen Sun, Kartik Alayrac, Cordelia Schmidt, and me. So what was the goal of the challenge? Is given a natural language query, we had to perform a ranking of all the video candidates. While the natural language queries were provided in raw text form, the video data was provided as extracted features from pre-trained models that we call experts. And we were getting 8 feature experts. We were getting 8 feature per video per expert. So now in video data, I mean, among all those features lies temporal information and cross-modal information. So we wanted to have a video encoder that would be able to extract cross-modal cues and temporal information from the video. So that's where our multimodal transformer comes into play. So it's a transformer encoder, similar to what is used for NLP task in Attention is All You Need by Vaswani and colleagues, except here we use video embeddings as inputs. And those video embeddings are composed of 3 elements that are summed together. First are the features. So here in this example, let's say we use 3 experts, okay, namely RGB, audio, and speech. Well, we'll provide those the 8 features that were extracted in the video, as well as max pooling aggregation of those features for each modality, for each expert. Then to this feature, we sum an embedding that we call expert embedding that will encode the information of which experts extracted those semantic features. And then we also sum temporal embedding, so T1 to T8, to encode the information of when in the video was the feature extracted. So the sum of these 3 elements gives us our video embeddings, and we provide those video embeddings to our multimodal transformer. And through the use of the self-attention mechanism, is going to be able, each feature will be able to pay attention to all the others, both across time and also across modalities. And at the end, we will only keep 3 embeddings, 1 per expert, and that will be our video representation. And then we integrate our multimodal transformer, so that's the whole part here on the right, into our cross-modal architecture. That is heavily inspired by the mixture of embedding experts by Miech and colleagues. So we've replaced the principal components here. So I just explained about the multimodal transformer. On the text side, on the caption side, we compute caption embedding using a pre-trained BERT model, the smallest available model for BERT. That's BERT base, and obtain a caption embedding. And then we project that caption embedding as many times as there are experts using gated embedding modules. And then for each expert, the similarity is computed as a cosine similarity between one expert representation on the video side and one expert representation on the caption side. And then we do a weighted sum of all those similarities using mixture weights that have been estimated from the caption embedding. And that weighted sum gives us the final output similarity that we use to perform the ranking of the candidate videos. So that was our approach for the Pentathlon challenge. Thank you for your attention. Do you have any questions?
Thank you for your great presentation. So let me see if there's some presentation, also some questions. So actually, I mean, I do have a lot of questions because actually it's very interesting because I'm flattered that it's really based on like the work that we have proposed like two years ago. And so in terms of you use like different mixture weights based on the language for like the different representation. And did you measure like the importance of the weights? I mean, did you try not using them and just like having just like an average or just a simple like concatenation? Or?
Yes, indeed. We tried just using like uniform weights, and it degrades the performance significantly. Also, what we've tried is actually computing those mixture weights from the video side, using like the class token from MMT, and we were getting similar results from like computing these mixture weights from the video side. So like we could compute both mixture weights from the caption side and from the video side, or just the caption side or just the video side. That gives pretty much the same performance, but not having mixture weights at all degrades the performance significantly.
Okay,
So,
and
yeah.
Okay, and for the language model, so did you try like, I mean, did you just use BERT because it's like very like, I mean, common, or did you also try to experiment with other type of approaches? Because I mean, personally, I know that it's very difficult to train. Sorry, go ahead.
Yeah, we've experimented with other models, like also a recent Grove model proposed recently that states that that BERT, I mean, several papers say that BERT is not doesn't provide good performance for visual tasks, but we found it was very important to fine-tune BERT, okay, because like several approach. They use the caption embedding, they extract the caption embedding from the class token without fine-tuning BERT. But that's not a task that BERT was trained on. I mean, it's just trained on mass tokens and also estimating if two consecutive sentences are contiguous in the corpus. But it's not at all trained on like summarizing the inputs. So fine-tuning BERT was really important. And yeah, we've experimented with NetVLAD approach from Glove, embeddings. We've tried many different approach, and using BERT actually is a huge boost for the performance. It's one of the biggest, it's one of the most important things in our approach is using BERT as a caption embedding.
Okay, so thank you very much for answering the question. And so if we don't have other questions, so we are going to move to the second talk.
From Renmin University of China.
Okay, it's working.
I'll present our solutions in the Video Pentathlon Challenge. The task of Video Pentathlon Challenge is text-to-video cross-model retrieval using provided multimodal features. The retrieval performances are evaluated across a pentathlon of 5 video text benchmarks. The evaluation metric is a geometric mean of different recall at case. Our contributions in the challenge are threefold. Firstly, I introduced the hierarchical video text matching method. Simple embeddings are inefficient to capture complicated video and textual details. Therefore, we employ the hierarchical graph reasoning model, HGR. The model decomposes video text matching into 3 hierarchical levels for events, actions, and entities to capture global to local information. We compare our HGR model with VSE plus and their encoding models. Our HGR model achieves the best performance on all datasets, especially on the DDMO and ActiveNet datasets, whose description lengths are relatively long, because the hierarchical matching is able to better capture fine-grained semantic information. Then I will introduce our enhanced inference methods. Query expansion is to reformulate a given query and ensemble all expanded queries to improve retrieval performance. In MSRVTT and MSVD, there are multiple textual queries to retrieve the same video. So we treat all queries of the same video as extensions for each other. We average cross-model similarities of all extensions in inference. Query expansion improves retrieval performance in the two datasets. However, the extended queries are from Guang-Chus annotations. It's interesting to explore other techniques for query expansions, such as automatic paraphrasing. We also observed that the learned embedding space suffers from the hardness problem. That is, some points have high probabilities to be nearest neighbors of many other points. So different queries are likely to retrieve the same hop videos. In order to mitigate the hardness problem, we leverage the inverted softmax algorithm in inference. It scales down the similarity between the text and the video if the video is also close to other textual queries. Our experimental results show that hardness mitigation can improve the naive nearest neighbor search by a large margin. We will further explore mitigating the hardness problem during training. Finally, we explore knowledge transfer methods to learn from additional datasets. Due to different dataset scales and cross-domain discrepancies, combining all datasets is not helpful according to our experiments. In order to benefit from additional training data, we first evaluate the most beneficial dataset for each target domain. We evaluate cross-dataset performance using the best HGR model. We can see that MSRVTT is most beneficial to others, which might result from the largest training size of the MSRVTT dataset. Therefore, we use MSRVTT as the additional dataset for each target domain. We explore a simple approach to transfer knowledge. We combine the target dataset and MSRVTT and bounce training examples from the two datasets. Experiments show that it is beneficial to employ additional datasets in training. However, we do not observe much improvements on MSRVTT when combining with others. It suggests that more effective approaches are required. For the final submission, our system is as follows. We use multitask balance training to train several HGR models and ensemble them. Then we employ query expansion and hardness mitigation inference algorithms. The result is as follows. We achieved the second place in the challenge. Here are some take-home messages. Firstly, the multi-level matching model is more effective than global or local matching models. Secondly, there exists a hardness problem in joint embedding space learning and needs to be addressed in training and inference. Finally, we only use a simple multitask training approach in this work, but it shows promising to further explore more effective knowledge transfer methods. Thank you for your attention. If you have any questions, please feel free to contact with me.
Okay, so thank you for the pre-recorded talk. So do we have any question on the chat? Okay, so I do have one question which is actually following the previous talk. So I mean, Valentin did mention that like using this broad-based language model did significantly improve a lot the performance of the final scores. And so it seems that you are using like, I mean, a very like, I mean, you are using a language model based on just glove word vectors. So did you try also using like, I mean, like more modern language model for the retrieval? And if yes, did it perform worse actually?
We haven't used BERT language models because due to the limited computational resources. The large difference I see the performance drop is on the UCOOK2 dataset, which contain many unusual words. So I think the large language models will be more beneficial on that dataset.
Okay, so which actually what was the language model at the end, because it was just an average of the word vectors, or?
Yeah, we just use global word vectors and LCMs.
Okay, I see. And so it seems also that from the report that you were, so did you use all the descriptor that we provided, or?
Excuse me?
Did you use all the video descriptors that we provided for the challenge?
Yeah, we just used all the training videos provided in the challenge.
Okay, and did you measure like if there was some features that were like more relevant than others, or like for the combination, like how did you combine
we just use the most strong features in different types, such the ResNet features is most strong in the image modality, so we just use the ResNet features for image modality. Yeah.
Okay.
And different modalities are just concatenated together.
Okay, I see. So if we don't have any other questions, so thank you again for attending at this late, I guess, time in China.
Thank you. Thank you.
And so we are going to move to the third place.
Good afternoon, ladies and gentlemen. It's my pleasure to give you this report. I'm Kaixu Cui from Xinhua Zhiyun Technological Limited. In this report, I will introduce the modes we used in the CVPR20 video Pentathlon challenge. The report mainly includes 3 parts: hybrid sequence encoder, dataset fields, capture ensemble. Our mode is mainly modified on the base of CE. Use hybrid sequence encoder to replace mean pooling, so as to extract more information, such as temporal information. In the train fields, we use dataset fields for pre-training. In the evaluation fields, we use capture ensemble to improve the score of some datasets. We use 2 hybrid sequence encoders. One is a dual encoder, and the other is to create gauge VLAD and gauge convolution network on the base of the dual encoder. For each module feature that has a sequence, we use hybrid sequence encoder to obtain the embedding. And for other module features that don't have a sequence, we use ETSO as the embedding. A module embedding are used as a CE input to obtain the similarity of video and caption. The first kind hybrid sequence encoder is the dual encoder. The second kind hybrid sequence encoder is to add gauge VLAD and gauge convolution network on the base of dual encoder. In the training phase, we use the dataset fields. We first fuse the 5 datasets for training, then evaluate the trained model on the 5 datasets. Select the best performing model of each dataset. At last, fine-tune the best performing model on the corresponding dataset. We found that each video of the MSVTT and MSVT datasets corresponds to multiple captions. So we use caption ensemble to obtain the similarity of the query and the video. Through experiments, we found that capturing sample can significantly improve the model performance on MSRVTT and MSVD. We evaluate on the value set provided by the organizer. From the results, we can see that almost has improved on the data sets other than U-2, but the result on the U-2 is not as good as using CE, which means result from too much the parameters cause the model to overfit on the training set of U-2. This is my full report. Thanks to all the participants and organizers.
Okay, so thank you for the pre-recorded talks.
Okay, everyone. So we're back after our relaxing break, and the next talk will be from Hazel from Bristol. And if we have audio transfer, okay?
Can you see my slides all right?
Yeah, that's great.
Right. Hi everyone, I'm Hazel from the University of Bristol. I'll be presenting our CVPR paper on action modifiers, learning from adverbs in instructional video. So there have been some recent works in instructional videos which aim to learn the key steps necessary to complete a task. So for instance, in making a meringue, you need to beat the egg whites, add the sugar, and spread the mixture before baking the meringue. However, these key steps aren't all you need to perform the task successfully. Some steps need to be performed in a certain way to achieve the desired outcome. So for instance, it's critical that you beat the egg whites quickly and add the sugar gradually and spread the mixture thickly so you get the right texture. So these caveats are often indicated by adverbs, as in these examples, and they describe how the action should be performed. So we aim to learn a representation for these adverbs, which generalizes across different actions and different tasks. And to do that, we propose to learn a video text embedding space, learned from weakly supervised action adverb pairs in the narrations of instructional videos. So our approach addresses two of the main challenges: learning from relevant parts of the video with weak supervision, and disentangling the action from the adverb so that the same adverb can modify multiple different actions. So how do we do that? Well, our input's an instructional video and the corresponding narration, and we've passed the narration to find actions from verbs such as roll and any corresponding adverbs to that verb, such as quickly. And we want to learn a video text embedding space where we can retrieve the relevant adverb for an action in the video or the relevant video for an action adverb pair. So therefore, we want the video and the action adverb pair to be close in the space. So in language, the same adverb can apply to multiple different actions, and it will modify each action in a similar way, even though each action is quite different. And we want our embedding space to reflect this property. So we disentangle the action and the adverb by first learning a good action embedding. And then we learn actions as what we call adverbs, as what we call action modifiers. So this is a transformation in the space that modifies the action. So in this case, it'll turn like a standard embedding of a roll into a roll quickly. So then the video ends up embedded close to the representation of the action modified by the adverb. And this action modifier gets shared between different actions. So hopefully we can learn a representation for quickly, which is not dependent on the action. So this would work well so far if we had some good supervision, but unfortunately instructional videos are only weakly supervised and only roughly aligned with their narration, and they contain multiple consecutive actions. So we need to learn the visual representation for the adverb quickly, only from the part of the video relevant to the action roll. So to do that, we collect some I3D features around the narration timestamp, and we want to learn some attention to find out which segments are relevant. So we propose to attend to the relevant video parts using scaled dot product attention, where the query is a projection of the action from the embedding space. So we use roll as a query, which allows us to find the video parts that displayed rolling, and then we learn what it means to roll quickly. So the action modifiers, the attention weights, and the embedding space are all learned jointly. So to do this, we made 83 tasks from the How-To Million dataset for action adverb pairs. And as ours is the first work to learn adverbs in a weakly supervised way, we're keeping the adverbs we learn relatively simple and just aim to learn 6 of the most common adverbs. So these are completely, partially, quickly, slowly, and coarsely, finely. And the challenge comes from learning these adverbs so they generalize across the 83 tasks and the 72 different actions within these tasks with the weak supervision. So here you can see an example of some of the variety in the alignment. So the top example is quite well aligned. However, some actions are quite long, such as the mix in the second row. And in others, the action's already finished before the narration occurs, as the fill in the third row. And then in some cases, the action happens off screen, like in the fourth row. So I'll just show you some qualitative results. So for each test video, we've got the original narration below the video, and then we'll pop up the predicted adverb when it comes. So here we know we want to find the action mix, but we want to predict how the adverb, so we want to predict how the mix is done. So the thickness of the border indicates the attention value. So you'll see it get thicker as the mixing starts to happen. And then from this part where it's got the high attention, we're able to predict the correct adverb. And we can do this across a variety of different actions. So here we've got another quick example, but this time it's turning. And you see the attention peaks when the turn happens. And then we're able to learn a good representation, which allows us to retrieve the correct adverb, ignoring any background segments and confounding actions, such as people talking, lifting up the plate. So thank you. I'll post a presentation on this as 10 a.m. tomorrow. So if you want any further discussion, please come to that.
So to me, some adverbs seems like should be quite sensitive to the video speed, like quickly or slowly. So I'm just wondering if we just play the video maybe in twice speed, will the prediction change from slowly to quickly?
We haven't tried just speeding up the video. That's a good idea because we weren't just focused on quickly and slowly. We had some other adverbs as well. We didn't specifically test that, but it's definitely an interesting thing to do. And I imagine it'll change because it does seem to predict when someone does stuff slowly. The question is whether it can pick up, because when it's doing it, it's like a natural slow action and a natural quick action. So if it's sped up, it might get some other artificial things which it doesn't quite recognize as being like a normal quickly, because like everything's a bit too quick, if that makes sense.
Yeah, that makes sense. I'm just thinking, try to understand whether the model actually tried to predict from seeing maybe the pose of the hand, those fine-grained detail, or just from the changing speed of the pixel value to predict this kind of adverbs here. So
yeah, it's an interesting one. I think a better example is like the completely partially, because you can't do that from necessarily all of the video. You're definitely focusing on a certain part of the thing, of the object.
Yeah. Another question here is, I can imagine this kind of action adverb pair might have a long tail distribution. So yeah. Do you use any kind of sampling strategy in the training to cope with that?
No, it's definitely an issue is that it's really long-tailed, and the way we learn the adverbs that share across these actions does seem to help on the long tail, because you've got your action adverb pairs are very long-tailed, but because you're learning the adverb as the same weights across all the different actions, that's what helps the long tail a bit. But we don't do any sort of particular balancing to fix it.
Yeah, that makes sense. Thanks for your answer.
Cheers.
Could I just ask also a brief question? Or I may have just missed this detail from the talk, which is, I guess some adverbs apply to subsets of things that they can't apply to everything. So do you have thoughts on the right kind of structure to be able to learn these mechanisms in a way that will like naturally allow the terms to only apply to subsets of the distribution?
Yeah, so we had that with so like finely coarsely is one which doesn't make sense. Like you sort of have something like thinly is very similar to finely, so like it kind of sometimes gets used interchangeably. So when it's like finely in one task, it might be similar to thinly in another, but at the moment it just assumes that you can learn the adverb for any task and doesn't work out whether it can make sense or not. We generally see if it doesn't make sense, it'll have like a retrieval of both of those like adverbs in the pair quite low compared to the other adverbs. But yeah, it'll still predict them as being a potential, which is obviously incorrect.
Cool. Thanks.
Cheers.
So now maybe we can switch to our next speaker. is Max Bain, who is a student from Oxford University. He will give a brief introduction about his work, Condensed Movie Story-Based Retrieval with Contextual Embedding.
Brilliant. Okay, awesome. Yeah, so I'm Max. I'm from VGG at Oxford, and this talk I'll be presenting our recent work, Condensed Movies, Story-Based Retrieval with Contextual Embeddings. And this is with co-authors Arsha Nagrani, Andrew Brown, and Andrew Zisserman. Okay, so what's the motivation? So there's been great advances in video understanding, and we've seen much of that today, but progress has largely focused on relatively short videos ranging from a few seconds to 20-second clips or so. In contrast, the average YouTube video is 11 minutes long, and the average movie or TV episode seen is 2 minutes long. Further, videos, at least in retrieval, are often treated independently, when in the real world, videos have context. And this context, at least for humans, helps a lot in understanding. For example, a TV or movie scene depends on the scenes leading up to it. Or I'm sure we've all watched a YouTube tutorial where the teacher first recommends we've watched a previous video, otherwise you won't really understand anything at all. So we'd really like our video models to take into account these this context. So let's take this clip from a movie, Trading Places, and a caption summarizing the clip, which is Billy reveals the truth to Louis about Duke's bet, which changed both their lives. Now this description actually contains references to things that have happened previously in the film. So Duke's bet happened roughly, it's like halfway through the film, and the part of the description which says changed both their lives. Now it's difficult to know their lives have changed without knowing what their lives were like earlier. So it might be possible to infer this just from the dialogue in the single clip alone, but at least for humans, the entire context helps a lot in understanding the clip. And so we'd like to have a model which can take into account this context. And in this work, we focused on text to video retrieval. So the standard setup is you have your text query, and you also have a video that you've proposed. And if this caption and video is the same, you want the similarity between these encodings to be high and low otherwise. In our work, we extend this. We devise a model which is inspired by a mixture of experts, and this not only encodes all the modalities of a video clip, but also encodes the context of other clips. So if you can see here, we have the Duke's, the clip I mentioned earlier, but it's also all the previous clips in the movie. And while this does look pretty complicated, all it is essentially adding another dimension to our features for the different modalities, which is like a video level feature. And the result of all of this is just, as always, just a similarity score between the text query and our current video clip. But this time it also includes all the videos before it as well. So to train and test this, we release a new data set called Condensed Movies, and this contains 34,000 caption clips from over 3,000 movies, and consists of over 1,000 hours of video footage. You'll be pleased to know it's freely available and fully licensed, so there's no download or copyright issues. And it contains pre-extracted features from 6 experts, nearly half a million annotated face tracks. And each movie contains roughly 10 clips, and these are indexed by their order in the film. And these clips are often the key moments in the storyline, and all the clips combined can kind of be seen as a condensed version of the movie. And this means the data set contains lots of movies, but is still able to be relatively lightweight in the number of hours, which a lot of movie data sets struggle with. They often maybe only have 200 or so movies. Our captions, the captions are also really rich, so they often have semantic information such as the intent of individuals, relationships between them, emotion, and also references to the past or future. So let's look at an example, and it wouldn't be much of a movie dataset presentation without spoilers. So if you haven't seen Karate Kid, I would look away now. So say we have this clip, and the corresponding caption is, despite illegal moves from the Cobra Kai that bring him to the ground, Daniel, who is Ralph Macchio, delivers one final kick and wins the championship. So if I just skip to here, we see the Cobra Kai member delivering an illegal move, bringing Daniel to the ground. And then later on in the fight, we see Daniel utilizing the crane kick position and delivering a final kick to his opponent, winning the championship, winning the fight and then the championship. And you can see this is a really hard, so it's a 2-minute clip, which is condensed down into just a single sentence. And there's a lot of things going on within the clip, and we think this could be an extra challenge to our current models. So in our paper, we actually show that adding the context of other clips actually boosts retrieval results for many different methods. And we think this task kind of utilizes almost like long-term narratives. But there's still a long way to go. So we still need better ways to encode 2-minute clips. So we found, unfortunately, just like average pooling across the 2 minutes was still performed the best. We tried a few things like NetBlad and so on, but I guess these approaches are quite heavy in the number of parameters, and models can overfit quite a lot. And we also think there's possibly more and better tasks to kind of test long-term video understanding. Yeah, and all the paper, data set, and features and code can be found at our website. And yeah, if there's any questions, thanks.
Thanks for the talk. I can skip and check whether any questions are coming.
Sure, yeah, no worries.
So, to me, I think considering storyline in the video retrieval setting is kind of interesting. You mentioned each clip can be considered as a key scene, which is around 2 minutes, and you have maybe around 10 clips in every movie. Yeah. So can I know, how do you pick those key scenes from the movie? Is that like randomly or uniformly sampled from the movie, or is there any other particular selection process to make sure each clip is more like self-contained as a concise story?
Yeah,
itself?
So that's a good question. So these clips are actually sourced from a YouTube channel called Fandango Movie Clips, and this is the largest movie. This is the largest collection of movie clips on the internet. Unfortunately, they've selected these key scenes in such a way that a viewer can watch all these 10 clips and they understand some sort of story. So we've been quite fortunate in like the collection bias that the curator has made these videos in such a way that they do tell a story in of themselves. And we think this is a good like middle ground, because our current methods are nowhere near understanding full-length movies. So maybe this is a bit closer to that.
Yeah. So another question here is, as you shown on the slide, you collect maybe around 400K face tracks in total. Yeah. So can you tell us more detail about how can we get these face tracks? Or, well, actually using this kind of face track contain a lot of maybe identity information actually help for solving the task, like what you say about the relationship or about different kind of things contained in your setting?
Yeah, that's a good question. So we release all the face tracks and the identities for the face tracks with the data set. We definitely think this helps. So we use the face features as an extra modality, an extra expert embedding in our retrieval context. And we think this can be useful because there's presumably a lot of biases in things like proper nouns. So, you know, someone like Billy is usually going to be a male. And we hope this sort of face embeddings can capture this. And there's maybe even more subtle things like emotion. But yeah, we need to definitely look into more of how these faces can be used. But yeah, yeah.
Thanks.
I think someone else asked, how were the captions collected? Yeah, so the on this movie clips channel, the videos actually come with captions, but they're quite. Let's find an example. They're kind of nestled quite deep, so we just used. So if I find it, if I just open it here. Okay, well, it's not showing, but yeah, it's included in the YouTube description, but we had to use some cleaning methods and some scraping methods to kind of extract this. Yeah, and these were made by writers on the channel, so they're all really high quality and professionally written.
So maybe one question from YouTube channel.
Yeah.
So the question is, just wondering how the dataset can be fully licensed if they are clips from movies. So how have you got around the copyright issues there?
So the movie channel is an official movie channel, like a source. So they have the license. So it's called Fandango, and so we're just using the videos, the clips released by them. So they have the license. Yeah. And so with our data set, we kind of release all the code for downloading these videos from YouTube and also trimming like the outro and all the cleaned metadata, cast lists, and so on.
Yes. Thanks for the talk again. And if there's no question anymore from the chat box, maybe let's move to the next part.
Thank you.
Thank you. Hello. Welcome back to our workshop, The End of End-to-End, a Video Understanding Pentathlon. So next, let's jump to the intro of our final keynote talk. Our final speaker of the day is Anna Rohrbach. She is currently a research scientist at UC Berkeley. She completed her PhD at Max Planck Institute for Informatics. Her research is at the intersection of vision and language, including a variety of tasks like image and video description, visual grounding, visual question answering, etc. We are very honored to have her present today. A quick reminder for the attendees, feel free to ask questions using the chat box, either in Zoom or YouTube. The speaker will answer your question after their talks. Let's welcome.
Thanks so much. Thanks for the introduction. And it's great to be with you virtually, even although, you know, we do what we can. So today I'd like to talk about how can we generate better stories based on video. And let's dive right in. So what I mean by stories here is not sort of storytelling that is sort of based off imagination, but stories about what we actually see in the video. So as humans, if we see this short video sequence, we can basically summarize it to ourselves as there is a singer who is playing a guitar, and there is a woman, Debbie, who brings Pete a bottle of beer, then they drink together, whatnot. So we can tell ourselves this little story. And what are some of the key features of how humans tell these stories or generate these descriptions is that naturally they are relevant to the video. So that's the requirement number one. And the stories will be coherent and they won't be redundant. So we won't be repeating the same information over and over. We'll be focusing each sentence on something new and interesting that's happening. And some of the anchors to which we sort of latch our story is these person identities around who the story evolves, like in this case, Debbie and Pete. And we also use co-references and pronouns and to make the entire story more fluent and more coherent. And of course, there is more than that. There is also other interesting aspects that we add to our stories. We talk about significant objects or places. We used, named entities like they meet at the Denny's. So a generic automatic system will not be able to generate such descriptions that make references to these, places that we may know as humans. Or it might even require some more understanding of common sense of what's happening in this present sequence of events. If we knew that this couple had a quarrel earlier, maybe now they are making up, and maybe this then brings, a new meaning, new significance to what we are seeing. And much more. There is a dialogue, there is audio, there is a lot happening in the scene, so which we are currently sort of not considering. So how can we make our automatic systems perform better and strive to make them towards this more human-like description generation of these longer sequences of video events. So today specifically, I want to talk about two projects. One where we aim to obtain more coherent, diverse, multi-sentence descriptions, and the other one where we want to connect descriptions to person identities. So let's dive in the first project. So let's consider another example. This is going to be not a movie, so just to give you an example of a generic video clip, this is some news segment. So there is some crowd on a raft and they have an accident and some people fall into the water and somebody runs to rescue. And so we see all this footage and all these descriptions. And although we can see that there is a lot of redundancy in the visual footage, the sentences themselves are fluent, diverse, coherent, so they are not repeating the same information over and over, that there are people in the water. However, if we look at our current state-of-the-art methods, they tend to, well, first of all, sometimes they make content errors. Then they tend to also make errors in terms of the fluency and generate somewhat inconsistent, incoherent sentences. Finally, they tend to repeat themselves over time, sort of repeat parts of the sentence or even entire sentences. And in this project, we'd like to focus on how to counter these issues and how to get a description that's more human-like. As you see below, sort of we mention interesting aspects like the people riding down a rough river, and there is maybe some footage in slow motion. So we are commenting on these more interesting details, yet try to still be relevant to the video. And to motivate our approach, we first quickly view what is the standard pipeline typically, right, for these captioning models. So we oftentimes use MLE training and train our generator with MLE objectives. And then at inference time, we use GriddyMax decoding or beam search to get our sentences. So the effect that this has is that this MLE training tends to favor more common, frequent n-grams and doesn't really tend to explore, the entire vocabulary space. So it's quite limited to the more confident, common concepts. Some prior work looked into how to counter this with GANs, and sort of the general story is that you train a discriminator, and then you can also so first you pre-train, then you train them jointly in an adversarial manner, and then finally you do the inference with this newly trained generator as before. However, people found that this training stage can be pretty unstable and challenging with the text generation models due to the discreteness of the output space. So what we thought was, well, we'd like to have the benefits of having this discriminator, but we want to avoid these issues with the training instability. And so we just skipped this adversarial training step, and we instead propose what we call adversarial inference. With a very simple idea, if we have our generator that's pre-trained, we can sample a number of candidates from this generator and then use a discriminator that would allow us to basically score these sentences and select the best one. So the main question remains as to how do you score? What is this discriminator? And so some prior works looked into this single discriminator that sort of tries to distinguish what is irrelevant to the video and also perhaps linguistically incoherent. Sort of, we decided to take a different approach. We call this a hybrid discriminator. So we wanted to specifically address each potential issue independently. So what I mean by that is, so let's say we have a number of samples, we want to score them, and we also have our previous sentence already predicted. So now how do we go about scoring these candidates? So we want them to be visually relevant, linguistically fluent, and also diverse and coherent across sentences. So therefore, we specifically design such discriminators. One is going to judge the visual relevance. For example, it will penalize The first sentence for mentioning kayaking, because there is no kayaking in this scene. The second language discriminator may penalize some linguistic incoherences, like in a raft, in a raft in this second sentence. Finally, the pairwise discriminator will compare the previous sentence with the current sentence and perhaps discover that they are redundant, and so score that low as well. And so finally, as we combine all three scores, we choose the best sentence out of our set of candidates. So we evaluated our approach on ActivityNet captions dataset. And first, we just looked at the standard metric used in most works, that's a Meteor score. And we don't really see that this score reflects that we are doing any better than the baselines. However, if we looked into more details, we see that our method has a much larger vocabulary size. It tends to generate more diverse descriptions. We look at the n-gram metrics here, and also it leads to less repetition. So all of these diversity scores combined, plus additionally we run human evaluation, which shows that our method basically is qualitatively leading to better descriptions than the baselines, but we can't rely on the Meteor score or other similar scores necessarily to reflect that. And just to give you another example, here we see a sequence of videos where it's pretty much just women dancing and at the gym, and the state of the art is kind of doesn't give us lots of detail or gives us some incorrect stuff about the man speaking to the camera, while our predictions are mentioning that they are moving in a synchronized manner, that using stepper, and so on. So this gives us much more detail and interesting description. So some of the takeaways from this first project is that adversarial inference could be seen as a much easier and more stable alternative to training GANs, and it seems to perform better in practice. That the design of the discriminator is important. We argued that we should decompose it into these three aspects. Perhaps there could be other aspects that could be added into this to achieve a certain other effects that you need. But evaluation can be challenging, so we rely on a mix of diversity scores, human evaluation, and automatic scores to kind of get a sense of how well we are doing. So all of that basically is towards getting more human-like, more interesting stories about video. So in the second part, I'd like to talk about a more recent project where we aim to connect video descriptions to person identities. And I first would like to highlight that in one of our earlier projects in 2017, we have actually tackled an extension to this kind of conventional pipeline where we have, a video clip and just get one sentence, someone strides to the window, and that's it. So we proposed a different task back then, which was we would consider a previous clip, and we actually looked into the ground truth sentence here, but only to gain knowledge as to who was present there. So we would know that, say, Sophia is present in that clip, and we would find where she is actually present. Sort of, we would ground that into the video, and then we would consider our current clip and generate a sentence and simultaneously ground both people that we mentioned, as well as introduce co-reference links to the previous clip. And so we aimed to go beyond this conventional setup, but we didn't really get to extend this to sequences of clips at once. And so in our most recent effort, we want to tackle a set of clips at once. And we introduced two new tasks in our LSMDC challenge recently. The description task, where we want to generate these sentences with the IDs in them, and the supporting task, where we want to fill in the IDs. And I'd like to first talk about this fill in the characters, and then explain how one can sort of piggyback the description through this supporting task. So first, let's look into what this task is about. So first, let's see what can we do as humans with these descriptions without seeing the video. So I want to motivate that this is an interesting task which requires complex reasoning and understanding of context to tackle. So we want to fill in these blanks, right, with the person IDs. So we can see in the first sentence, his brow furrowed, blank looks down at the ground, that this is a male. So let's just label this person 1. And then blank eyes him angrily, her jaw clenched. So it seems to be a female, so naturally a different person, person 2. And finally, blank heads off. Here we really don't have a good intuition to which person this may be. We need more context, or we need a vision to solve this. So let's say we have additional context. Blank folds her arms. So this is a female again, so we could hypothesize this is person 2. And we can then combine all this knowledge together to figure out that this the person who heads off is person 1. This is already getting somewhat shaky, so we're doing some guessing here. Finally, blank approaches blank, who leans against the wall of the house. Again, based on what we've seen so far, if this was person 1, this could be person 1 and person 3 that hasn't been seen previously. And so based off text alone, we can do quite some guesswork, but it would be much more robust and reliable if we could actually access the video and see these people and analyze, whether we are matching the right IDs together. So this is just to illustrate that this task requires reasoning about a set of clips and descriptions jointly. And language is quite strong and gives us useful cues, but we still need video to solve this problem. So we have annotated every person mentioned in the descriptions with the ID, as well as every he and she pronoun. So we basically now have all of these IDs annotated, as well as the genders. And we split our movies into sets of 5 clips. So some interesting statistics on the distribution of these IDs, because we are looking at the local sequences of 5 clips, they tend to contain maybe up to 4 or 5 distinct IDs, and in rare cases, more than that, so up to 11 within the scope of 5 sentences, right? Now, how do we address this task? So our inspiration here comes from like what I showed you, that once as humans, when we aim to solve this problem, we really go back and forth, we compare these different sentences, we go back and forth, we look at the clip to understand who is being talked about. So we are kind of solving it all jointly, rather than just relying on set of local decisions about to match or not to match some blanks together. So that motivates our approach, where we want to represent our blanks in a certain multimodal representation S, and then we would feed in these representations S sequentially into our transformer and sort of jointly infer in a sequence-to-sequence manner the set of person IDs. That is a high-level kind of overview. Now, how do we get these representations as specifically? Well, we'll be looking into the face clusters and the features that describe them. We also consider other video features and the blank encodings. And so the main idea here is to introduce an attention mechanism that would, conditioning on the blank, select the right appropriate visual feature, specifically find the right facial clusters to focus on, and then use this attended visual representation jointly with the blank embedding as our representation S here. And we also experimented with additional gender prediction objectives, both on the language side as a pre-training scheme for our embedding, and on the visual side, where we want to be able to infer the gender of the person based on just the visual feature. And these are both helpful. So how do we evaluate this task? So we propose the following metric. We consider that it's important here to do an evaluation on a pairwise basis. So we have a set of ground truth IDs and we have a set of predicted IDs, and we want to basically consider all pairs in each set. And then we for instance, here we have this arc between these two IDs. I'm not sure if you can see my mouse. The first top two IDs, so they are distinct, and they are also distinct in the ground truth. So they are different IDs. Therefore, we count this as a correct prediction. Now there is a big arc at the far right where we incorrectly linked person one, while ground truth tells us these are distinct IDs. So this will be counted as a mistake. And in this manner, we evaluate our predictions, and we say compute an accuracy 4 out of 6. So next, we want to see some information about how our data is actually distributed in terms of these pairs that match and don't match. And for that, it's very simple. We can actually just try two straightforward baselines. One is always predicting person one, so same ID, and another one always predicts all different IDs, like 1, 2, 3, 4, 5, and so on. And so both of these guys together gives us 100% accuracy. So that means that 60% of the time we have to, cut the link, and the remaining 40% of the time we have to link the two IDs. So among all the pairs in our data set. So that's just kind of gives us the feeling of how the data is itself distributed. And now when we try adding, so here we now compare the text-only version of our model and the full model with vision, and we see that the improvement we are getting from vision here is not huge, but that there is still an improvement. And we can further discuss that in the following. We also compared to two state-of-the-art methods from our challenge last year, which we outperform both of them. So both of these methods sort of are based on this intuition of making more like local decisions about pairs of blanks. Well, like I said, in our method, we argue we want to make more of a joint inference about all these IDs together. Now, humans who have not seen the video, who have to solve this task without video, can do pretty well and better than all of these methods. And if we zoom out, humans who do see the video are doing much better. So what this tells us is, well, there is a large room for improvement, but also that video is really important for humans to solve this task. So video signal has to be really important, but our models are not yet doing a very good job exploiting this information. And some interesting insights about our method versus the other two methods in terms of the predicted IDs. We see how they're distributed, and we see that our method in orange here captures much closer the ground truth distribution in blue than the two other methods. So they tend to underlink in certain cases and generate new unseen IDs. And here is an example of that happening. So we have two people here, person 1 and 2, as you see in the ground truth appearing in this sequence, and our method correctly establishes all these links. And so here are some typical errors that we found. And Yu et al., they introduced a new person P3, and they correctly link it to herself, but they basically it's a new character that doesn't actually appear in this sequence. And then they yet in the last clip they introduced yet another character 4 and 5, again failing to establish the linking. And Brown et al. Here make the similar mistake. And like I want to kind of come back to where I motivated this task from. We want to generate identity-aware video descriptions. So what we can do now with this tool in our hands, we can generate sentences with someone with any method of your choice, and then apply our fill in the characters model to it, and essentially introduce all this ID information, which makes these much more informative and much more useful. We can also add gender prediction as well, if that's required. So this is sort of where we are right now in terms of linking video descriptions and ID information. So some of the takeaways from this part is that this task of filling in the characters allows for automatic evaluation, yet it's an important test of multimodal understanding of sentences and video events. So I encourage you to check it out. And it enables us to do description with the ideas as well. I think we've seen that the transformer design here was effective in terms of predicting these ideas, but we also see a large room for improvement. And I think some of the issues worth considering here are we need to make use of more localized, both spatially and temporally, visual representations, I believe, which would provide us sort of better grounding into the events and characters who are acting in these scenes. And we have to make more effective use of visual modalities. So perhaps these two go hand in hand, perhaps with more grounded representations, more relevant to this domain as well, we will be able to get a more significant boost over the language-only models. And I'd like to make one more point here, that we can do all this step-by-step reasoning, which can be quite complex, as we've seen as humans. Can these models do it? I believe to a small extent they do with this transformer design, but I think there is still a long way to go to actually ensure that they can do this complex reasoning. So to sum up, I've been talking about our method for more natural, coherent and diverse descriptions of visual sequences. And then I talked about our fill in the characters task and how we can also do description with the identities. So some of the other issues, like I mentioned in the beginning of the talk, that remain open and really need all your creativity is how do we incorporate significant concepts, objects, places into these stories, named entities, deeper sense of understanding of the events, sort of more about emotional states of the characters or other common sense notions of when somebody is having a quarrel or making up after the quarrel and so on, and other modalities as well. So I think there is lots of interesting directions to explore in this space. Yeah, so please go check out. We have the code out for the first project. We have a challenge still open for the second project, and reach out with any questions. Yeah, and thanks for your attention. Yeah, I'm happy to take any questions if there are right now.
Thanks for the great talk. I can skim and check whether we have any question from the chat box.
Yes, please. I can't really see the chat right now, so if you can navigate that.
So for the first question is, for the captioning work, I personally like those kind of multiple discriminator design.
Mm-hmm.
As discussed, each of the discriminator measure different things, such as visual relevance, linguistic fluent, and something like that. So how can we get the ground truth for each of these metric in the training time?
So, okay, I haven't talked about the details of how we train these discriminators. So to train each discriminator, we had to design specific sets of positive and negative examples for each of them. So one sort of simple thing is you're combining as positives a sentence that actually matches the video, and as a negative, a non-matching sentence. Or if you want to measure fluency, you can combine, you can say this is a fluent sentence from the human description, and now we can corrupt it perhaps in some way and make that as a negative. And we experimented with different kind of corruption techniques and so on. And so basically we have to design these positives and negatives for each discriminator.
Okay, that makes sense. So another question from Mako in Zoom is, the fill in the blank task could be thought of as a form of person re-ID, in that you want to find when a character reappears later in the scene. So have you tried any of those approaches as a baseline for this task?
Just the re-ID, just like purely vision-based. So we have vision baselines, vision-only baselines, where we would take the entire sequence, we would sort of detect well, we anyway do that. We detect all the faces in this set. Then we did some clustering to group the like faces together. And then we sort of tried to do frequency-based picking of the cluster as a to fill in the blank. So we evaluated that, and that is inferior to the multimodal approaches and even just to language-only approaches. Because I think it's really important to also understand what's going on in the sentence. You cannot just rely on visual similarities here to understand how the blanks need to be filled out. So you can get somewhere in terms of the linking on the visual side, but that won't answer the question how to fill in the blanks themselves, if that makes sense.
Yeah. So I personally really like the task of filling in the characters. So I think it's kind of super useful to review the storyline of a movie. So it's kind of interesting to see that comparing with the human performance, the current model performance is not so great. To me, there might be several factors, like maybe we do not actually have perfect face detection at the beginning, or we do not pay a correct attention to fill the correct blank, or maybe we do not have a perfect face descriptor to match the face and do the final prediction. So do you have any analysis to try to split this kind of error types and have some any idea which type of the error current dominant the current performance?
It's an interesting question. I guess in the spirit of the workshop, the end of end-to-end, some of these require fairly complex pipelines, and like in some of the earlier works as well. So detection, tracking, feature extraction, which allows you to link appearance. You are just kind of losing performance across many of these. And it's sometimes pretty hard to say how much exactly you're losing. So I would estimate that the accuracy of the clustering itself is perhaps somewhere around 80 to 90%. Like that would be my guess. At least that we tried to evaluate that in some of the previous projects, not specifically, I believe, in this one, but that's kind of, I guess, where we are. But then in movies, there are challenging situations, like some of them I've shown you, where we see the person from behind, or we see at a very challenging viewpoints. And so, or like very big changes in scale. Sometimes we see them extremely zoomed in, and other times they're very small. So there are challenges where maybe other data sets which have sort of more uniform appearances, sort of not everything is going to work really well in movies. In terms of trying to debug this pipeline and kind of reveal whether we are attending to the right character, I think that's interesting too. So when we have this attention mechanism internally in the system, but it's also slightly challenging to fully debug that, because it's attending over a set of clusters, and sort of the noise tends to accumulate. So I think it would be great to clean that up and sort of be able to ground explicitly in this project as well, as we tried in some of the earlier works. So that's a long answer to a complicated question.
Quite valuable.
I have a question, but in this, I don't want to stop the flow. Okay, thanks a lot for the talk. That was very interesting. Mine is actually, I guess, somewhat related to Yang's, also about understanding the performance of the model. You mentioned on your penultimate slide about how to solve the task as a human, it often involves several complicated reasoning steps. And I was wondering if you thought that the current architecture, if we were to scale up the data more, do you think it would be possible for it in its current form to perform that kind of reasoning? And maybe if you've done any studies along the lines of plotting a graph where you restrict to a subset of the training data, and to see how performance grows as you scale the amount of data you give to the model?
No, we have not, I believe. Let me think. Not really.
Or even if just sort of intuitively, if you think it's very data bound, or
I think definitely with more data we will see some improvement, but I think it's also about perhaps better. So I think the current bottleneck is probably the multimodal fusion itself, and how we integrate visual information and the language information. So from some of the experience we had in the past, also in the fill in the blank tasks, but not with IDs, just like filling in the blanks in sentences, any blanks, we found that the most improvement we would get with better fusion techniques, essentially. So I think that's where I would place my bet. Right now, yeah, and just features, visual features, which we are using, some of them come from very different domains. So there might be an issue with that as well, where we are losing some of the performance. So something that's more, even in a weakly supervised manner, but adapted to our movie domain, I think could be helpful. Yeah, so on the language side, we are doing pretty well. I feel like it's really the vision that's lacking here. And perhaps any additional supervision that we could introduce, even a small amount of supervision, like we would actually say, okay, here is the actual phase that you need to care about, and sort of that could go a long way. So I would advocate for semi-supervised setup to boost this.
Thanks again. So if there's no more question, I think maybe we can move forward to the conclusion of this workshop. Thanks again, Anna. That is a great talk.
Thank you.
So given the time in hand, I will just wrap up for today's discussion. We had an amazing set of speakers and panelists. Thank you all for your insightful talks and the kind discussion today. We also host a challenge that focused on learning from videos and languages with pre-extracted experts across a site of 5 influential video datasets as a part of this Pentathlon of the video understanding. Huge congratulations again to the challenge winners as well as the runners-ups. I would also like to thank all the organizers. Without all your efforts, nothing would have been possible here. So thank you for helping with preparing the data for the challenge and analyzing the results, inviting those amazing speakers to this workshop and advertising as well. So last but super importantly, all the organizers want to thank the audience attending our workshop, taking part into the live discussion today. I guess that's all for today's discussion. Hope you will enjoy the rest of the CVPR this year. Bye.